Hello, everyone. Welcome to our Cisco Certified Network Associate Bootcamp. My name is Michael Gibbs, and I'm the founder and CEO of Go Cloud Architects and Go Cloud Careers. And I'm so happy to be here with all of you today to talk about networking. So, this is a free Cisco Certified Network Associate, a CCNA 200-301 boot camp, and we are going to cover an entire Cisco Certified Network Associate curriculum. My name is Michael Gibbs, and I've been working in technology now for about 25 years. And you know where I spent most of my life? In networking. Let me tell you a little bit about my networking background, then we'll talk about what we're going to do today, and we'll talk about some of the kinds of training we're going to offer. I am one of the original Cisco Certified Internet Experts. In fact, when I took my Cisco Certified Internet Expert exam, it was a 2-day exam. My number is 7417, and we started counting at 1028 because Cisco thought it would be cool to start counting at 2 to the 10th. So after about 3 million people that attempted Cisco certifications before me, I was the 6,400th guy to pass the Cisco exam. So you know exactly how long I've been in networking. And in these last 20 years, I have trained more cloud architects, more network engineers, more network administrators and systems administrators than I can possibly even imagine. And networking is so essential. Networking is critical. And this is networking skills training. And whether you're a cloud architect, you're going to need this networking skills training. Or if you want to be a network engineer, you're still going to need these networking skills training. So while we're going to talk about Cisco networking essentials, and it looks like network engineer training, and it looks like network administrator training, which it is, guess what? It is also cloud architect training because networking is one of those critical cloud architect skills. So for your cloud career, for your networking career, we're here. What is a computer network? We'll talk about. This is an intro to networking course, and we are going to talk about networking and cloud computing for the next 2 weeks. It's going to take us 2 weeks to do it because there's so much content here. When we look at the AWS Advanced Networking, we can drop that into about 300 pages. When we're talking about this, it's talking about 2,000 pages. So this is going to be deep, even though it's beginners. Letting you know the format, we're going to go for 3 to 4 hours per day, every day, Tuesday through Friday this week and Tuesday through Friday next week. We will have lectures, we will have slides, and we will have a lot of labs. That's right, you heard me. We will be doing a lot of labs. And here's why. When we talk about routing, I want you to see the packets move through the network. When we talk about BGP, even though it's not part of the CCNA curriculum, but if you guys want some BGP, let me know and say BGP. And you know what? We'll probably do an extra session to talk about BGP because I want to make sure you can all get that network architect job, network engineer job, solution architect job, cloud architect job, or any kind of networking you want. So this is free network training provided by Go Cloud Architects and Go Cloud Careers. So as we begin, I want to give you some guidelines. There is a very good book, in fact, 2 books, and they're written by a gentleman named Odom. He works for Cisco, and he wrote the books for Cisco Press. He's an old school CCI like me, a very old school. We recommend that everybody buy the 2 Cisco Press books that are written by Vernal Odom. My team will pop a link to these books. They are the perfect complement to this. Guess what? Cisco made the test. Cisco hired one of its own people to write it. This is the book. This is the one you recommend, and we always recommend going to the source. So how are we going to do this? We're going to run our course in the following way. We are going to be teaching our material, but we are going to use the same structure as the official Cisco Press books. So if you follow our course and you read that book, if you're stuck on one section of the course, guess what? You can also refer to that book. Watch our course multiple times because we're going to leave it here for permanently, and marry that with the book. You will get the full experience. We're going to run this like a traditional $5,000 boot camp, and that's what a good boot camp like this costs. If you were to buy it from Global Knowledge or Cisco. When I was at Cisco, I used to teach systems engineers about service-oriented network architectures and how to design high-performance, high-availability systems. So I've been teaching networking to networking professionals now for 2 decades at some of the world's biggest networking companies. WorldCom, now Verizon. Comcast, I was teaching networking to networking engineers. Riverstone Networks, which is now Nokia, I was teaching networking to networking engineers. And I was even teaching the systems engineers at Cisco Networking. So that's how long I've been teaching networking. So we're going to have fun. How are we going to run this? The following manner: 20 minutes content, 10 minutes of questions. Now, we have a lot of labs. Now, most of the labs start to when we get to about chapter 4 or 5 of our materials. But if you guys are getting bored, I'll throw labs in sooner because I want you all to become the best network engineers, network administrators, cloud architects, solutions architects, or whatever you desire. So we are going to have fun. We're going to do lots of labs. Let me know 2 things before we get started. Type hashtag CCNA. And then, while you're at it, right, hashtag CCNA 200-301. Get those 2 hashtags there and let's get ready. If you're watching this content and for some reason while you're watching this content, it feels like you're totally lost, please refresh your browser, because what happens if you join it at a different time or you paused it, we could be in one location and you guys could be in another location. And by doing that, you know what's going to happen? We're going to miss. So I want to make sure that all of you guys make sure you get everything done. So we're super excited to have you here. Now, there are people that have blue wrenches next to their name. These blue wrenches are special friends to Go Cloud Architects. They could be Go Cloud Architects employees, or they could be some of our best students you can possibly imagine. And they're there to help out as well, to make sure that you all have a wonderful, wonderful, wonderful CCNA bootcamp experience. So this is our free CCNA 200-301 course, the Cisco Certified Network Associate. And let's get everybody CCNA qualified. And most importantly, let's make sure you have the knowledge to be successful as a network architect, network administrator, cloud architect, solution architect, or enterprise architect. So let's get to the fun. So to begin, what is networking? And networking is just really the interconnection of devices. And that's all it is. But it's the plumbing that makes everything possible. So if I want to send a message to Chris from my team, I have 2 options. I could drive the message over there, I could fax the message to him, or I could send it over a network. Now, I've worked on all kinds of networks. We used to work on IPX networks and AppleTalk networks, and you name it. There were lots of networking protocols. But guess what? It's simple and elegant for you guys today. There's just one. There's only a single networking protocol that we're working with. Life gets so easy. It's just one single networking protocol and protocol stack. It's TCP/IP that we're talking about, and that's what we're going to be working on. So in this first chapter, in this introduction, we're going to talk about a perspective and a history on networking. Then we'll talk about the TCP/IP networking model, and then we'll talk about data encapsulation. We're going to set the foundation for the things that are to come. So big foundation, got a lot of stuff to talk about. Again, remember, CCNA is about 2,000 pages of official reading. The AWS Certified Solution Architect Professional is about 500 pages of reading or less. So it's about 4 times the depth of that. So we're going to build some technical competency for you guys here. So let's begin with talking about this. Realistically speaking, with enterprise networking, you're going to be dealing with data centers, etc., and users. And that's really what we're talking about. Now, let's kind of look at it, what networking used to look like. And this was kind of, the world where I came from. So let me show you about the old school networking days. When I started, what happened is you'd have these companies that basically were their own autonomous systems called the cloud, a cloud, a cloud. And what happened is we all just connected everybody's cloud together. And that was the foundation of a network. But they were all these little discontiguous clouds. So you had the government cloud, the ARPANET, and then you had some educational units, and they would just connect to each other. Well, fast forward a couple of years, in the 90s, guess what? We had more use of the cloud. Now businesses were starting to use it. So what were these clouds they were using in those days for connectivity? They were frame relay, they were ATN, they were BGP VPNs, there were all kinds of stuff. But predominantly the clouds in 1990 were frame relay and ATN. And then around 2000, we got to this concept of the single cloud. What was the single cloud? It's called the internet, which is basically a whole bunch of dissimilar networks that all run their own internal routing protocols that are connected via BGP. That's it. That's what modern networking is. A whole bunch of individual entities that are glued together with BGP. And, we maybe do some BGP concept. So let's talk about this concept of the TCP/IP model. Now, here's the thing. I don't use this, never have. I use the Open Systems Interconnect model, and we're going to talk about that in depth. But I just want you to know right now, there are two models for TCP/IP networking. There's this old model. And if you ever hear people talk about the link, the internet, the transport, and the application, that's the old model. And what's wrong with the old model? Well, network engineers and architects across the world use the OSI model. That has, and we'll go over it in depth. The physical layer, which is the wire. The network layer, which is the card. The data link layer, which is the card. The network layer, which is the IP address. And the transport layer, which is basically TCP, IP, UDP, etc. When we look at this old thing was some weird theoretical academic model, but we all use the OSI model. Guess what? Layer 1 physical, layer 2 data link, layer 3 network, layer 4 transport. The students we have are really great cloud architects in our cloud architect career development program, and they say there's 7 layers, and I say, yeah, but we only care about 4. And they say, why? I say, is networking is just the wire, the card, the IP address, and the routing protocols, and the transport layer. The rest of us as networking people, we don't care. Networking people, we're not using web pages. We're building plumbing. Networking people, we don't, use applications. And when people ask me how to set stuff up, they're like, Mike, I don't understand. You can design a network with 500,000 employees, 200,000 routes on the routing table, and it's nothing for you, but you can't figure out how to use them because networking people to work on layers 1 through 4. So keep that in the back of your mind when we're talking about these things. Now, when we talk about these kind of protocols, let's think about it. When I say physical layer, I'm talking about a wire. So this is a physical layer protocol. This little earphone set to my iPhones, this is physical layer. It transmits what? Electrons. If it was a fiber optic cable, what would we be transporting? Photons or light. No difference. So if we think about the physical layer, think about the cable. When we think about the data link layer, think about the Ethernet card that's in your computer that you plug the cable into. When we talk about the internet, the network layer, we're talking about the IP address. And when we're talking about transport, we're talking about TCP, UDP. And if you're going to follow the internet model, the one I just showed you, guess what? At layer 7, you've got your applications, such as your web pages, your email, etc. That's what we're talking about. So let's talk a little bit about how this concept of networking works. It's based upon a logic. It's based upon a logic of, let's say you go to your computer and you say, I want to go to www.gocloudcareers.com. You request that from the server on a specific port, and the server responds to you. So let's think about this. We do a request to the DHCP server. I want to go to www.gocloudcareers.com to learn about cloud architect training. So we send the request. The web server sends a response. The web server sends another response. We keep sending data. Now, what a beautiful system until data is lost. So when we're dealing with networking, and we're going to get in much more depth throughout the course, but we're just introducing some concepts. When we're dealing with networking, we have 2 ways that we can send information. We can send it reliably, or non-reliably. And let's really talk about what that means. So I see Abigail Marks is on there with one of the blue wrenches. If I say to Abigail Marks, Abigail, meet me at XYZ location at 4 p.m., I know Abigail for a fact is going to say, Michael, I got it. I'm going to meet you at XYZ location at this time. And I'll say, confirmed. I know full well that Abigail heard me, and I know she's going to be back. That's why she's got one of the blue wrenches. She's incredibly reliable. But the key is that's what's clear. I send a message and she responds. Now, watch what happens, how magical this is. So you go to www.gocloudcareers.com. You send a request. You get a response. Packet 2 is sent to you. Packet 3 is sent to you. Hey, wait, packet 2 is not delivered. See, it got lost. The computer itself, because it's TCP, sends a message back to the web server. Hey, guess what? Sequence number 2, message number 2, I lost it, please resend. Now think about that. Data comes in, you lose it in the transfer, and you ask for it back. Wow. Talk about getting things to be reliable. So if I want to send a 10 terabyte file to somebody, I send message 1. They say got message 1. I said message 2. They say got message 2. I say here's messages 3, 4, and 5. And they say got messages 3, 4, and 5. And I say I've sent you messages 5 through 10, and they only got 5, 6, and 7. They say we need messages 8, 9, and 10, and we retransmit them. So TCP/IP, Transport Control Protocol, is used for reliable data transmission. Reliable data transmission. If you see this on a test, TCP is used for reliable data transmission. And we'll talk about times when you don't want reliable data transmission, because there's a lot of times where this would be a problem. But for right now, realize when things are critical, we're using TCP/IP. Send a file, TCP/IP. Bank transfer, TCP/IP. Writing an e-prescription, TCP/IP, because we need to know that the whole message and its integrity was delivered. So, how does communication occur on the network? You got a wire on both sides, so that's called same layer communication. Now you've got an Ethernet card on both sides. That's same layer. So what's happening is each layer is communicating with each other, and the adjacent layers are communicating with each other. And that's really how this works. So I know right now we're talking high level, and we're going to get into much deeper concepts, but let's imagine we're going to the post office. Let's say here, this is my local post office in Palm Beach, Florida, right near where I'm at. And this is me over here. I want to send a letter. So in order to send a letter to my friend in New York, what do I need to know? I need to know his name, his physical address, the number of his house, the city, the state, and the postal code. Why? Well, if I want to send this to Nick Pappas over there in New York, and when I'm trying to send a message to Nick Pappas, if I'm not careful, if I go to Astoria, Queens, where there's a lot of Greek people, and I'm Greek, my family's Greek, but if I go to Astoria, Queens, where there's thousands of Greek people, guess what? I might find 300 Nick Pappases. So if I want to send a letter to my cousin Nick Pappas, as opposed to somebody else's cousin Nick Pappas, clearly I'm going to have a problem, right? And that's why every device on the internet needs a unique IP address, so you know how to send things. So everybody has a unique IP address. So there's a Nick Pappas that lives at 123 Main Street in Port St. Lucie, Florida. There's a Nick Pappas that lives at 16 Pine Bark Lane in Holland, Pennsylvania. There is a Nick Pappas that lives at 3224 48th Street, New York, New York. Postal code this. So that when we go to the letter, what do? We take the letter to the post office that sends it to the network. It then drops it off at one post office, to another post office, to another post office, to another post office, until Nick Pappas gets the letter. And Nick Pappas calls me on the phone and he says, guess what, Mike? I got your letter. Wow, it was really nice. Thank you. That's how it works. So keep that in the back of your mind. Each one of these post offices along the way is an intermediate stop. Guess what? In networking, we go to locations along the way, and I'll show you how you're going to trace your way through the network when we do labs, and it's going to be cool and fun. But keep that in your mind. That's how the post office does things. So since in tech, we don't invent anything. We just take the old stuff. We basically smack a new name on it, modified a new thing, and we're good. So let's look at basic routing. Here's what it's going to look like. Here we go. We've got Larry over here that wants to reach Bob over here at 1.1.1.1. So Larry doesn't know what to do. Larry looks in its routing table and says, I have a default gateway that points to router 1. And then router 1 says, hey, Larry wanted to go to Bob. I now have Bob's message over here on router 1. How do I get to the subnet 1.1.1.1, which is probably a /32? And router 1 says, hey, I know what to do. In my routing table, it says send out this WAN interface to router 2. Router 2 says, do I have a route to 2.2.2? And it says, ding, 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 ding. I have it. It's right over here out this interface. So what does the router do? Router 2 sends it to 3, Bob. Now it's on Bob's computer. Bob's computer has to answer. Does Bob have a route to Larry? No, but does Bob have a default gateway in his routing table? Yes. So Bob sends his data over here to router 2. Router 2 says, do I have a route to get to Larry? And it says, yes, I do. Go out this link to router 1. Router 1 says, do I have a link to Larry? And it says, yes, go out this interface. And then Larry and Bob are talking to each other. That's how it happens. That's exactly how it happens. And what you see here, which we're going to talk about in much more length, is see how you have an IP packet? Then you basically have the transmission control protocol header, and then you've got another header related to the type of packet that it is. So that gives you some guidance of what's going on. And so, for example, we've got it. Let's talk about encapsulation. Every layer, in fact, let's talk about encapsulation for a minute. So every layer in networking talks to the previous layer. So think about it this way. You got an electrical signal, right? That's basically electrons. Now, as we move up a layer, we're transmitting frames. So now we've got the data, which has now got an Ethernet frame attached to it. Then we go up to the network layer, we smack an IP header on it. Then we go to the transport layer and we smack a TCP, UDP, or ICMP header. So with each level of the stack, what we're actually talking about, we're encapsulating and decapsulating. So let's go back to our picture over here. In this particular environment, we've got our data and we're adding Ethernet. So there's always overhead of what we're adding. So let's try to look at it from another angle. The physical layer, we're transmitting bits, which are really in the form of electrons. The data link layer, we've got our data link header. At the network layer, we've got our IP header. At our transport layer, we've got the TCP header. So as you can see, even as we go from data at the top of the application layer moving down, we have to add headers and encapsulations. So each layer talks to the other layer. Now, I know this is the least fun amount of content in the entire program, but we have to talk about it, so please bear with me. It's just very important content, even if it's not the most fun stuff in the world. But it is pretty important stuff, so let's keep talking about it. So now let's looking at the perspectives of encapsulation. You can see segment is layer 4. Packet is layer 3. So what do we have here? We have data TCP. So now when it gets to this layer, we're going to have TCP, data, and IP. And then we get to the Ethernet layer, what are we going to have? We're going to have TCP, IDP. We're going to have TCP, data, TCP, data, IP, and then we're going to smack an Ethernet header on it. So now you know how that works. Okay, so let's talk about the OSI model. And we'll talk about it a little bit. This is a pretty important academic model for us to go over, so just bear with me. Realistically, what we're talking about here is as follows. In networking, we've divided the entire world into 7 layers. And this is called the Open Systems Interconnect model. And this, just so you let you know, is what all networking people use throughout the entire world. All networking people use this TCP/IP model. And what does that actually mean? It means as following. It means that every layer will talk to every other layer on both sides of the network. So physical layer talks to physical layer. Data link talks to data link. Network talks to network. Transport talks to transport. So let's look at the layers. Physical layer, wire. Data link layer, Wi-Fi or your Ethernet card. Network layer, the IP address, the routing protocols that we're talking about. Transport layer, TCP or UDP. Session layer, we're really talking about sockets, but we don't touch this as network architects, network engineers. Presentation layer, we do nothing here. Now, understand that while we do nothing at the presentation layer, that's where things like TLS encryption occur. And then the application layer is what people use when they go to the web browser to go visit a YouTube video, or when you go to a web browser to look at photos of my beautiful cat Cindy, who everybody knows she's world famous because she likes to chew Ethernet cables, unplug servers, unplug routers, firewalls, run on keyboards, and she's a pleasure to have around the office. I mean, she's truly amazing. But there's that. So kind of keep that in the back of your mind. So let's talk about a little bit more at these layers so you know them once and you never forget them. So I'm not a big acronym fan. I'm a big understanding fan, but a lot of people like to say all people seem to need data processing, and that's the way they remember it. So, application layer. Guess what? Application layer is is where you use the user stuff. Presentation layer, guess what? Is as follows. Present the data to the application layer and other stuff. So what kind of stuff goes on here? ASCII text, binary things, JPEGs, encryption, that's presentation layer stuff. Session layer, this layer defines how to start, control, and end the conversations. It includes control management of the bidirectional messages that are being sent. Transport layer, this is where your TCP is. This layer provides control of the data that's being sent from point A to point B. So TCP, send and resend, or UDP, just send once and then don't resend. And there's a time where you need both, and we'll talk about that. If you did TCP or reliable over voice or video, you'd have a massive problem. We'll talk about why when the time comes. And yes, some of the concepts we'll probably get into will be CCIE level, and some of the concepts will also be on CCNP level as we do things way above the CCNA, but we have to. And here's the reason. There's a massive difference between certification and getting hired, and I want you all getting hired. So we're biased towards the things that are going to get you hired. So kind of keep that in the back of your mind. Okay, so let's talk about, actually, we've spent about 20 minutes, so let's do the following. Let's see if anybody has any kind of questions, and we'll open it up for about 20 minutes of questions, and we'll get to chapter 2, and we'll talk about the fundamentals of Ethernet LANs. And that should be a really good time for a lot of people. And then at some point, we're going to start doing some labs, hopefully today, but if not, we have labs scheduled for every other day this week. So if you've got some questions, Chris, let's bring in some questions. I'll answer some questions for about 10 minutes, and I want to get back to the content. But I want to make sure everyone's having a good time and no one's lost. Can an IP address be spoofed, Angelo? Absolutely. And that's why we use next generation firewalls. We do stateful packet inspection, and we do a tremendous amount of things because, yes, absolutely. We'll talk about man-in-the-middle attacks and other things during the security section. Chris, you can bring in the next one. The routing protocol BGP has application layer, but what we're doing is all network layer stuff. PR. Good question, though. Chris, you can bring in the next one. At layer 2, what protections are against IP spoofing? Angelo, layer 2. There are no protections against IP spoofing at layer 2. At layer 2, you can do MAC address spoofing. You can do layer 2 access control lists. You can do private VLANs. You can segment via VLANs. You can do layer 2 access lists. You can do 802.1x authentication. At each layer, guess what? We've got different level things. So at layer 3, we can deal with IP things. At layer 2, we can deal with MAC address things, and lots of security there. Now, if you're on the cloud, Angelo, realize you lose most of these great security benefits because they do it and don't give you access to these things. But remember, layer 2, which is in a VLAN or a switch or an Ethernet card, that kind of stuff, we do layer 2 MAC address spoofing and layer 2 MAC address filters and layer 2 things, not IP things. We have to do whatever's in the layer. But that's a good question. Chris, you want to bring in the next one? What is frame relay and ATM? So the first clouds were like this. We would connect you to a cloud and we would create a virtual link for you in multiple locations. The first one that I worked was actually something called frame relay. It was a very slow, old school networking technique. In fact, the frame relay was pretty much T1 lines, which were 1.54 megabit per second, E1 lines, which were about 2.048 megabits per second, or they were fractional. They'd be 64K links, and that was all we were dealing with. That was frame relay. Now, what happened is frame relay was slow, but the cloud concept worked so well. of just connecting to this thing that can connect anybody to anybody that we came up with another cloud called ATM, asynchronous transfer mode. And that was an optical cloud. And we could get to speeds like OC192, which was 10 gigs. And I was working with this cloud and these 10 gig links about 20 years ago. So you can imagine how fast these links were, these OC192 links. But they're just old school WAN and cloud technologies. Great question there. Why do you focus on 4 layers, Ryan? Because that's all networking is. Networking isn't software engineering. Networking isn't using applications. Networking is simply the wires, the cards, and the communications protocol to get them there. That's all of networking. So it's kind of like, why does a race car driver not learn how to fly a plane? Because race car drivers drive race cars versus pilots that fly planes. Networking is extremely specific. And we focus on those 1 to 4 layers. And Ryan, I could give you 500,000 pages of reading that only focus on those 4 layers, and you'd still need to learn 80% more after 500,000 pages of reading in 25 years. And that's why networking people like me, my world is focused on BGP. And even BGP is a big chunk of networking. And that's enough to build an entire career, just knowing BGP. In fact, you could build a career in a subset of BGP by being so good at it. Great question there, Ryan. I think we have time for 1 or 2 more, Chris. Hey, Mike, application layer is so much confusing to me. Why is BGP considered application layer? Okay, an application is only this. An application is something that does something. So when you get on your cell phone and you click Slack, that's an application. When you get on your cell phone and you text message somebody, that's an application. BGP itself is an application, but we don't use the application. What we use is the networking features of the application. Network layer reachability. Send me a community and match the community and prepend the AS path. Send a community and change the weight. Send a community and change the local preference. Filter or route with a distribute list, a mount path. Everything that we do as network engineers is layer 3. So, sure, you've got a camera. The camera itself you could call layer 7, but the film you could call layer 3. And the photographer only uses layer 3 and down. Now, if you hand it to a movie producer that's going to take the film and edit it, they have another job. But network engineers, we don't touch applications. We don't do any of that. Layers 1, 2, 3, and 4, that's all we do. That's our whole world. Okay, good. Good PR. Excellent. So, Chris, I think we have about 4 or 5 minutes before the next set of questions. Rohit, what's the difference between frames and packets? Great question. At layer 2, we have frames, which are layer 2, and at layer 3, we have packets. That's it. What's the difference? Remember, we go from a packet, which basically is going to have the TCP or UDP header, the data, and the IP header, to the frame, which is going to have the TCP header or the UDP header, the data, and the IP header. And now it's going to have we're going to smack an Ethernet header on it, and now it'll be a frame. Does a layer 3 switch have the same capability as a router? A layer 3 switch is a router. A layer 2 switch is a switch. What happened was we used to separate them, and then we decided to put them in the same device for speed and performance. Is there a difference between TCP and UDP frames? Well, there is no such thing as a TCP or UDP frame. We have frames at layer 2, we have packets at layer 3, and we have segments at layer 4. And yes, there is a difference because they're basically using a different transport control protocol. And we'll get to much more of that throughout the course. What is the difference between UDP? TCP is used for reliable transport, meaning I send something and you say, yes, I got it. I send you something else and I say, you got it. UDP is me just sending you data as fast as possible and hoping you get it. And there's a time and a place for that, which we'll cover throughout the course. Great question there, Mohammed. How does the sender know the MAC address of the receiver? Sadie, good question, and we're going to talk about that. There's a protocol called ARP, or Address Resolution Protocol, where when a host wants to say something, it says, ARP, who has the MAC address for this specific IP address? And it's a big screaming broadcast. And of course, we've got a whole chapter dedicated to that. What do I mean when the layers really talk to each other? Explain in simple language. Okay, so you've got a wire, and you send electrons on the wire. And then you go up to an Ethernet card and you plug a cable between them, and they communicate via the Ethernet format because they're Ethernet cards. Then you have an IP address. That's like a physical address on your house. And the routers route packets to each other based upon their IP address. So you've got a transport layer, which determines whether you ask to see if it's retried or not, and they use the same segment. So I hope I answered your question there. Each layer talks to each other in the layer that it matters. If it's a fiber optic cable, it's going to be photons or laser or light that goes across the wire. That's what we mean. Chris, I think we can probably do one more. Okay, so if you're new to networking, there's a couple of things. I do want you to buy the book that we talked about, the official Cisco terminology book. Now, I'm not using any jargon at all. I'm just using the industry standard terms. So, if you don't know, please look the terms up. Please follow along. Chances are all these questions that you're going to ask, we're going to get to in another section. We just haven't got to it yet. We have 1,000 slides and we're on like 30 something. So we've got a lot that we have to get to yet. And then it'll become familiar as we go through the concepts. So unfortunately, I can't I can't spend 8 hours on every specific word, but if you bear with us throughout the time, we're going to get through the content if you just keep paying attention. And we will get through that content and it will become abundantly clear to you. But, I don't get any benefit when I say, hey, buy a Cisco Press book. I'm not an affiliate to anybody. I don't get paid anything. I just want you to go to the official sources. I worked for Cisco for a decade. I'm an official source. The Vernal Odom that I talked about is an official source. Cisco paid him to write this book to prepare you for the exam. So where do you think they're going to get their exam questions from? That Cisco book. But I get no benefit from it. I just want you all to be maximally successful. That's why I'm recommending somebody else's product other than mine. Combine mine with theirs and you will have extremely good success. And like I said, I get no benefit out of it, but I get the benefit of knowing you all get hired. So let's talk a little bit about local area networks and kind of keep that in the back of your mind. And as architects, we are front and center. We try not to hide behind slides. I know engineers like to do that, but I'm an architect and I want to teach you how to present naturally, not hiding from behind the corner of a slide. There are times where I have no choice but to do it, but that's a last resort. If any of you guys have architecture careers in the future, make sure you know you can't hide in the corner of a slide unless you have absolutely no choice. So that's why we'll be out there front and center the whole time, because I want you to learn how to do it the way we want you to do it to get cloud hired or network hired. So let's talk about what is a local area network. A local area network is just this: communication in a small area. So your house, a physical campus, are all different forms of local area networks. And they all look a lot different. We'll show you some basic networks, what they're going to look like. So at the basic smallest element of the world, this is a small office, home office network. Bear with me 1 second so I can find, okay, here we go. So in this particular environment, let's look at a small office. Now this might be something you've seen before. You go into the office, they've got one router to the internet, plugged into a switch, or it has an integrated switch, and there's a couple of ports on it. Guess what? This is your Starbucks. This is my home. Well, not really, because I've got enterprise-grade firewalls and IDS and IPS systems and enterprise-grade switches, not this. But as a general rule, this is your small office, home office, your doctor's office, your Starbucks. It looks just like this. Now, it's a wired LAN. Anything that matters should not be on wireless. I'm going to say this again. Anything that matters should not be on wireless. Guess what? Anything that matters should never be auto anything. Anything that matters, you'll statically hard code IP addresses. You will statically set the speed and duplex of your ports, and we will get to that in extreme knowledge. But keep that in the back of your mind. We have to do these kind of things. So This is a small office. Now, this is an even smaller office with Wi-Fi. Basically, you've got a router. The router typically controls an access point, which is a layer 2 wireless device that enables your users to work. And that's your pretty typical types of environment. And what is the medium for this? How are they communicating? Some flavor of Ethernet. So let's talk about Ethernet standards, because there's a couple of standards. So in the old days, people like me got to work with these 10 megabit per second Ethernet networks, and wow, they were fast for us in those days. Because remember, we were dealing with like 64K WAN lines at best. So 10 megabit per second was huge, but this was 10 base T. It used to be coaxial cable, or it could have been Cat5 cable. And the standard for this was 802.3. That's the standard of internet. All internet standards are 802.3. Okay, so then, now mind you, when these things were 10 megabits per second, I was working in networking. The routers, a big $5,000 Cisco 2500 series router could pass a massive 1.5 megabits per second of throughput. So this router was 6 times faster, this Ethernet port, than the routers could do in those days. So then we had bigger routers, and we had fast Ethernet ports, which were 100 megabit per second. And then we had incredible speed. We had these fiber optic connections that could go a gigabit per second over fiber optics. That was your 802.3C. And I remember putting these things in with the optics in these switches, and wow, it was fast, high performance, and we were all excited. So that was kind of cool. Then, and it looks like my screen is freezing. Then we came out with gigabit per second things that we could use with a coaxial cable with Cat5 and Cat6. And then we came out with 10 gigabit per second ports, fiber optic. And now my computer has two 10 gigabit RJ45 copper ports. How amazing is that? It shows you how fast we've gone. So we've really, really gone fast. So let's talk a little bit about this. Let's talk about the way Ethernet frames work. So at layer 3, we have packets. At layer 2, we have frames, and frames are a little bit different. So let's talk about these frames. Here's actually, my screen is completely frozen. It doesn't look like I can share both right now. Okay, can you? Yeah, I'm moving around now. Okay, so what ultimately happens is you send data to a switch. Can you guys see me in real time? Chris, could you let me know? Because it looks to me like my screen's freezing. Chris, could you let me know? And if I have to change the bandwidth settings, I will. Am I moving around okay? Can you guys see that? Bear with me. I'm going to try and lower the bitrate setting in case we have some network congestion. Okay, as long as it looks okay for you guys, because for me, what I'm seeing, it looks like I'm frozen. Am I frozen,
Mike,
Chris?
we're not seeing any problems on my end.
Okay. Well, then I won't worry about what I'm seeing on the monitor here. Okay, so the way this is going to work is it's going to work as follows. It's going to look like this. Your computer is going to be sending data to the switch. The switch, realistically speaking, is going to be in a position where if it doesn't know what to do, it's going to literally forward the frame out all ports except the port that it came in on. And then if the switch doesn't know what to do, it's going to forward the port to all ports except for the one it came in on, and then it's going to forward it to the host. Everyone, please bear with me. I actually can barely move my mouse here right now. Something's frozen on my system. Let me try and eject one of the RAID arrays I have. I think that could be causing me a problem. Let me see if I can pull it. Okay, I'm going to try this and see if I can get through this. And if not, I'm going to have to do a system reboot because I'm having a really hard time trying to move my mouse. So in this situation, what's going to happen is you're going to have a PC that's going to be sending frames to the switch. Now the switch will look and say, do I have a MAC address in my MAC address table? And if it does, it knows where to send it. And if it doesn't know where to send it, it's going to send it out all ports until the port that it came in on. And that's exactly the way that's going to work. Okay, so the way this works is you're going to have a set of wires. And I've never made an Ethernet cable in my life in 25 years because I'm an architect and architects don't do that. But tremendous number of people that I know and lots of network engineers and all network administrators are going to do this at some point in their career. And basically what's going to happen is you're going to have a wire and it's going to have a pair of, And on one side you'll be transmitting and another side you'll be receiving. And that's why you can transmit and receive at the same time, which gives you something called full duplex, the ability to send and receive at the complete and total same time. So let's talk about the components that make this possible. Each device has its card, the card that occurs in the data link layer. You plug in the card to the data link layer, it goes into the node, and they communicate with each other. And you've got a set of wires, transmit and receive. So let's talk about this. And I may go for a system reboot in a second because my system's literally freezing every 3 seconds. And I'm not sure if I can continue. So I may do a reboot in about 30 seconds. So let's talk about what these RJ45 connectors and ports look like. Well, I'm sure you've seen one of these Ethernet wires in your own house. And for example, I'm sure you have an Ethernet card in the back of your computer. And also, I'm sure you've plugged into a switch. And that's really what it looks like. Now, there's all kinds of switches, but that's your RJ45 port. Now, if you're dealing with a switch, and the switch could be any kind of switch, it could be one of these switches, note, there's an optical port attached. And those switches can be they can be something that looks like this. Here's another switch that I have sitting in back. What you'll notice is all these ports are RJ45, and these are 10 gigabit per second uplink ports that are fiber optic. You stick a laser in them. So let's do this. My system is 100% frozen. Chris, could you aggregate questions while I do a system reboot, and then I'm going to come right back?
Yes, I will be here, and I will share pictures of Cindy the cat with everybody.
Okay. There are pictures of the cat. I aggregate stuff. My computer is freezing to the point where I can't even click on anything to go through slides.
All right. Okay, so Mike is having some technical difficulties. Ironically, as somebody pointed out, while we are discussing internet speeds. So essentially, he's going to turn it off and turn it on again, and we'll see if that works. As we all know, that's usually the the easiest solution. So let's see if I can find some pictures of the most likely culprit of our issues. Give me just 1 second here. I will find us some pictures. Maybe not. I'm usually prepared with pictures of the cat. So let's go here. All right. And if any of the blue wrenches would be nice enough to help me find some questions, that would be great. That way we can make sure we take care of some questions when everyone gets back. All right, so let's find a picture of Cindy. So here is the culprit of all of our problems. Cindy, she is such a cute cat. She normally is found in Mike's lap or at Mike's feet. And apparently today she's probably chewing some Ethernet cables. But that is Cindy. If anybody has ever wondered what Cindy the cat looks like and who is our #1 intern here at Go Cloud Careers, it is Cindy. Let's see here. So I'll stop sharing that. All right. Is everybody able to hear me? I see that LM says he can't hear me. So if you could share in the chat box there with me if you can hear me. I like that. I always liked Scottie Pippen better than Michael Jordan when I was growing up. So thank you for that, Angelo. Mike is Jordan and I am Scottie. All right. So let's see. All right. And all right. So this is Cindy's friend Sunny. Sunny is the elder architect. She is 11. Cindy is, I believe she's a year old now. So Sunny tries to keep Cindy in line, but apparently Sunny has not been able to do that today. All right, so let's see if Mike is back. Let's add him into the stream. All right, Mike, are you there?
Thanks, for taking over, Chris. Yeah, Cindy has been actively unplugging things all day, and that's usually where most of my network problems come from. The little gremlin that runs on my keyboard gives me lots of spelling errors, chews through my Ethernet cables, unplugs RAID arrays, and guess what? Now we're back. So my 64 computer with a half a terabyte of RAM and 3 NVMe drives and a RAID array to give me speed couldn't apparently handle our YouTube session. So let's have some fun. So let's get back into the training content over here. Apologies for, Windows not doing what Windows was supposed to do. It's just part of life.
So did we reach a stopping point for questions, or did you have some content to continue before we get to the questions?
Let's do this. Let's take some questions now because I feel like we interrupted the natural flow. Answer 5 minutes of questions and get back to the content.
All right.
Because weird stuff happens every once in a while when you're dealing with tech. I've got a lifetime of tech, and let me tell you, what can go wrong will go wrong. It's really just a matter of just doing the best you can. So I'm glad everybody's still here. Thank you all for waiting, and let's do some questions real fast, and then we'll get into there.
All right.
Cat hired. I love it, Millicent. Yes, Cindy has been hired. Sunny is hired as well. And yes, we love our furry friends around here.
All right.
So a switch is a device that enables you to plug a lot of devices into a single subnet. And we'll talk about subnets, and we'll talk about switches versus router, but a switch is where you plug all your devices in to the network. Good question. Chris, you want to bring in the next one? Are there any prerequisites for these lectures? No. The Cisco Certified Network Associate is a foundational level, but we have 8 3 to 4 hour days. So we're going to cover it all. But again, remember, cloud computing is silly easy. The reason people are going to cloud computing is because they have less management worries about the network. But here's the thing. If you don't worry about the network in your cloud computing environment, everything falls apart. So there's no way of getting around the networking thing. If you want to be a network engineer, network architect, and if you want to be an actual cloud architect or solution architect and actually work and get paid and have a good job, you have to know this networking. So we're starting at the bare minimum 0, and we're going to work our way up very, very significant. Coming quick.
The next one's not quite a question, but I found it hilarious.
Okay. Yes, there is a cat that is eating my Cat 5, 6, and 7 cables. Yes, absolutely. How is the TCP protocol responsible for error correction? Eva Doikia, what a question. So, Chris, I want you to acknowledge messages. Chris is now the computer on the other end. Chris, I sent you a picture of Sunny. Did you get it?
Yes. So cute.
Chris, I sent you a picture of Cindy and Sunny this time. Did you get them?
Yes. Yes.
Chris, I sent you a picture of Cindy and Sunday. Did you get it? Chris, I sent you a picture of Cindy and Sunny. Did you get it? Okay. Chris didn't get that. I'm going to resend the data to Chris. So that's what TCP is, and that's why it's reliable. Because what happens is in about 3 seconds, Chris is going to say, hey, Mike, do you mean to send me anything more? I got your first 2 packets, but not the last one. That's exactly how TCP does error correction. But there is also something on there called the frame check sequence and a CRC code that's also going to tell us if things are damaged along the way. Can I please explain about the session layer? The hashed. I am a network architect and a network engineer. I just told you that network architects and engineers only do layer 1, 2, 3, and 4. We have nothing to do with the session layer. So in 25 years, I've got no experience with the session layer because guess what? I'm a networking person. We don't touch the session layer. Yeah, I probably should check my fans for cat hair. They're in a lot of places. Kylie, what a beautiful cat you have there. What a pristine, beautiful Siamese cat.
And I feel like this is prescient because it was your first thing to do. Troubleshooting 101.
Yeah, absolutely.
Yes. Yes. That's the old
It
show.
really is. Now, if it's a router, we're not going to be doing that. With the router, we're going to be looking at the routing table and doing trace routes, etc. But with a hobbyist router that you would have your home, yeah, reboot it. With a Cisco or a Juniper router, no, we're going to get in deep and figuring out what's going on. But you know what? Somewhere along the line, we're going to reboot it. And I got to tell you, that'll fix 20% of the problems. The problem is you can't always do a reboot in a production environment. Yeah, there actually is only 2 pairs that you're going to use, and we're going to talk about that coming very soon. Again, I've never made an Ethernet wire because I'm a network architect, not an engineer. But guess what? We'll talk about those 2 pins coming up very soon. Of course, Terminator 365. I used to teach these courses for Cisco. I used to teach Cisco engineers, and I've been teaching engineers for 20 years. I've gotten more people Cisco certified. This is enough. It's more than enough. This is the same as if you paid Cisco $5,000 to take the week's class. You're having it being taught by an ex-Cisco employee. It's identical. So yes. Routers don't use spanning tree. Routers use layer 3, so we don't have that problem with layer 3. Throughput is the amount of stuff you can shove through there. The bit rate and the data rate is the amount of stuff you're shoving through there. They're very similar. Meaning I could have a throughput, I could have the ability to do 100 gigabit per second throughput, but my application may only be streaming at 10 gigabit per second, so I have 90 gigabit left over. That's the bit rate. Good question there. Yeah, I'm more used to debugging, but I got to tell you, after having a cat around, I do more debugging from the cat than other things. Thank you, Angela. My video feels better. I could see on my screen and then I couldn't figure out why, because my GPU was only at 30%, my CPU was only at 4%, and my memory, I still had almost a full half a terabyte, but don't know why it's working though. Can you apply spanning tree on a router? You would never apply spanning tree on a router. Well, the whole point of using a router is so you don't have to use spanning tree. And you can route between subnets as opposed to bridging. Spanning tree is the ugliest thing. I will tell you that I spent a career removing spanning tree and replacing it with layer 3 links. Yes, we're going to leave these recordings on YouTube.
Sorry, I didn't mean to interrupt you. My finger got a little happy there.
That's okay. No, but we're going to leave these questions on YouTube. And these are good questions. Sadie, as a cloud network engineer, yes, you need to know layer 1. Yes, you need a layer 2. Yes, you need to know layer 3. And yes, you need to know layer 4. Because if you really want to be a cloud networking engineer, you're going to be setting up software-defined networks to the cloud, BGP to the cloud. You're going to be prepending ASs, changing the weights of ASs. So you're going to need a whole lot more than just the CCNA as a cloud network engineer. You're going to need somewhere between the level of the CCNP and the CCIA level knowledge to be acceptable. Yes, absolutely. How many times does TCP retry? Well, that's based on how you code your application. But we network architects don't worry about that. We worry about layers 1, 2, 3, and 4. This is absolutely live. How long is this course? Great question. If you signed up for the course, you would know that we're having this course for 3 to 4 hours per day for 2 weeks straight on Tuesday through Friday. Where do the lost packets go? They just disappear. They reach their time to live and they just die out. What resources do you think are enough for passing? The resources that I recommend are the official Cisco Pressbook and this course and nothing else. The official Cisco Pressbooks that we listed and provided a link for in the beginning of the class, they're what we recommend, and we recommend this. Those two is the perfect combination. Okay, so Angela, we can do copper or we can do fiber. It's our choice. Most switches use optical networking ports for 10 gig, and the reason they do is twisted pair is only good for 100 meters, and copper and fiber optics can go for miles and miles and miles. So people assume that you need from switch to switch communication, longer cables, longer distances, and you always do it via fiber for those reasons, because you could have an Ethernet WAN, etc. That's a very solid question there. And Chris, I think we can do one more, and then we got to get back to the content.
All right.
Why should there be no specific stuff on wireless? Because wireless is incredibly unreliable. If you basically take your phone, make it the Wi-Fi access point for your PC, and then do an extended ping to Cisco for about an hour, you'll notice that you're going to lose about 5% of your data or more. You're going to notice that some of your data takes 2 milliseconds and some of your data takes 200 milliseconds, and the connectivity is going to be horrible. Also, wireless is what's called the shared medium, and we'll talk at some point about hubs and collisions. So if you've got 1 gigabit wireless, it's only good for 100 megabit due to collisions and people transmitting, retransmitting. So wireless is never used for anything that matters. Neither is auto. Okay, so let's get back to the content. Actually, before we do that, if you can type hashtag CCNA in the window, I know you're all here and paying attention.
I want to thank everybody for letting me entertain you with pictures of the cats. If you have any pictures of cats or dogs or gerbils or hamsters or chinchillas or zebras or anything that's a pet that you're legally allowed to have, please send them to admin@gocloudcareers.net. Admin@gocloudcareers.net. You can also send any questions that you might have for us. But send a picture of your pet also.
So going back to this, when we're dealing with Ethernet, we're dealing with twisted pair cables. And basically, you've got one for send, which goes transmit to receive, and one for receive, which goes to the transmit on the other side. And that's why we can talk in full direction at both times. Transmit wire, receive wire. If not, like the old days, like wireless, we transmit, and if we're trying to transmit and trying to receive at the same time, our data collides and we have to start all over again. It's really, really ugly. So this is why we're dealing with twisted pair. Now, a straight through cable, which is normal, is going to have pin 1, which goes to pin 1 on the other side. Pin 2, which goes to pin 2 on the other side. Pin 3 and pin 6, they all talk to each other on the same side. This is called the straight through cable. Why? You plug your PC into a switch, you plug your router into a switch, and that's the way this is supposed to work. They communicate via the switch. Now, if you want to connect a router to another router or a switch to another switch, that changes everything. So I'm going to look at this one more time. Switch to device. Straight cable, same pins on both sides. But if you want to go from router to router or switch to switch, then we have to change everything. We have to flip those cables, and that's called a crossover cable. So router to host, straight through cable. Host to switch, straight through cable. Router to switch, straight through cable. Network device to network device, crossover cable. PC to PC without a switch, crossover cable. So straight through anything that connects through a switch. So how's that going to work? Router plugs into this port, switch plugs into this port, everybody's happy. But if this switch plugs into another switch, we need a crossover cable. Assuming it's on a copper port, not fiber optic. Don't put heavy metal things on your head. It's not good for your neck. So here's an example. Switch to switch, we're running crossover cables. And you can actually see what the wires physically look like with a straight cable. And here you can see what some fiber optic cables look like. I'm not a layer 1 guy. I've been a layer 3 guy my whole career. But what you're dealing with when you're dealing with copper is you're dealing with the core. This is where your laser sends the light. And then you're dealing with basically something that protects it. And then you're dealing with something else that protects it, something that makes it strong, and then a jacket. So that's how your stuff is kept from falling apart. Kind of keep that in the back of your mind. And you can see you've got your photons that are pushing through the core of this. Again, I am not a layer 1 person, but kind of keep that in the back of your mind. So people ask, why are we doing fiber for some and then copper for others? And here's the reason why. With Ethernet, we're good for 100 meters. Everybody say it. Ethernet, Cat 5, Cat 6, Cat 7, 100 meters. Now, what if you have a campus and you've got a kilometer between both buildings? Well, guess what? It's still local, but now we can't use copper. What if you have 200 meters between buildings? Guess what? We still can't use copper. I mean, we could take a 100-meter cable, plug it into a switch, and then plug it into another cable. I guess we could do that, but then we'd be sticking a switch in the parking lot or burying it underground, so that's no good. So for any distance that matters, what do we use? Fiber. So let's look at the different kinds of fiber. When we deal with single mode fiber, we can go long distances. When we go multi-mode fiber, it's short distances. Why don't we always just use single mode fiber? Cost. Multi-mode fiber is cheaper by far. So what do we use? In the office, we use things like multi-mode fiber because it gives us good speed and performance. But look, that's good for 300 meters, 400 meters, not much. What if we want to go to the internet's point of presence, 10 kilometers, that's 6 miles, that's better. How about this, 30 kilometers or 18 miles, that's getting better. So as you can see, we're using fiber for long. So let's think about the cloud environment. We want to create a direct connection to AT&T or an express connection to Azure. What do? We get a single mode fiber connection to the direct connection location. And we connect that to another switch with a simple cable. And then from there, it gets called back to the AWS network or the Azure network, all on this long distance fiber optic kind of connections. And I'm not really sure what I just did there, but it made it look pretty ugly, but we are back to the normal. So, now you understand that. Now let's look at a different kind of cabling. Let's look at the cost of it. The copper cables, cheap. The multi-mode fiber, you're starting to pay for it. Single mode fiber, this is getting expensive. Now let's talk about the part on the switch. Copper port's cheap, cheap, cheap. Multi-mode, you've got to buy a laser, an optic. It's starting to get expensive. Single mode, you could be paying thousands of dollars for the port. Going back to the distance, copper, 100 meters. Multi-mode, no big deal, half of a kilometer. Single mode, wow, you've got some distance here. So copper, electrical signaling interference. Laser, none. So switch-to-switch communication. Do you want to risk crosstalk on wires or electrical interference? Oh no, your switch-to-switch links are critical. So that's why you're using fiber optics between switches. So let's look into the Ethernet frame, because you do need to know this. This is what your frames look like. So letting you know, any frame less than 64 bytes is called a runt. Any frame less than 64 bytes is called a runt. Any frame above 1500 bytes is called a giant. Any byte above 1500 bytes is a giant. So if anything less than 64 bits is called a runt, which is not good, and anything that's above 1500 bits is called a giant or a jumbo frame. Keep that in the back of your mind. If you have a network and you've got a frame that's 2000 bytes and your network can't support a payload of 2000 bytes, guess what? Everything falls apart. So you must know what's in your frames and your frame size and your header size. But less than 64 bytes, not right. Greater than 1500, specialty frames, you must tell the network to be able to accommodate them or else it won't. So what goes into this header? You've got a preamble which tells you something. This is the destination MAC address. This is the source MAC address. This gives you some information. Here's your data, and here's what's called the frame check sequence. It basically is like a hash, something that shows you if the message has been damaged in the process. So that's kind of what we're talking about. So reading it through another way, the preamble does some synchronization of the messages. The starter frame delimiter begins to tell you the destination MAC address. In the source MAC address, we can see the center of the frame. The type will tell us whether it's IPv4 versus IPv6. The data is obviously how much kind of data you put there. And then the frame check sequence is really about making sure your data got there in an undamaged manner. So just kind of keep that in the back of your mind, and then you're going to have a really good kind of concept. So let's talk a little bit about MAC addresses. So every device that you have has a hardware address. In frame relay, we had a layer 2 address, and it was called a DELC. In Ethernet, we have a layer 2 address, and it's called the MAC address. So if you bear with me, if you go to a command prompt or a terminal prompt on your computer, if it's Windows, type CMD on your computer. If you're on a Linux or Unix system, type ifconfig. So if I do an ipconfig/all on Windows, that will tell me what? It'll tell me, go do this on your computer, ipconfig/all or ifconfig in a terminal. Right now, you can see, if I look at mine, I can see my IP address. I can see that my MAC address is as follows: Foxtrot Charlie -34-9 Alpha 0 Foxtrot Delta -16. That is the MAC address on my computer. It is a physically hard-coded address on your computer. While we're at it, everybody, type your own MAC address in the chat box so I know that you've known the layer 2 MAC address of your system. Type your MAC address, type MAC address, and then list your MAC address, and then I know every one of you, and no, we can't connect to you on your MAC address. Your MAC address is way behind your routers, and then we know that you've got it. So keep that in the back of your mind. ipconfig/all, you'll see it. You'll see your MAC address. So let me give you an example of what it's going to look like. Got a user over here. User is sending data. Push. It gets to a switch. The switch works by looking at MAC addresses. So the switch will do this. If the switch knows the MAC address, it will send it directly out the port. If the switch does not know MAC addresses, it will flood out of every single port that it has. So data gets to switch 1 floods it out of everywhere, floods out of switch 2 to computer 3. Computer 3 says, I have this MAC address. Switch 3 puts it in the routing table, or the MAC address table. They call it a content accessible memory, or CAM table, so it knows which port to send it. So what does it look like? Let's say over here, we're back to my trusty rusty switch. Basically, a packet comes into the switch on this port, and it's destined for MAC address Foxtrot Charlie -34-9 Alpha 0 Foxtrot Delta -16. And let's say the request comes in on this port, it'll get flooded out on every other port on the switch. And then all of a sudden, this computer will say, I have that MAC address, and then the switch will know to send it directly out that port and no other ports. So good job. I see lots of you guys have found your MAC addresses. Woohoo! You found it. Now you know. Guess what? While you're at it, you can probably see your IP address there too, right next to it. You'll be able to see your subnet mask. You'll be able to see your DNS servers, and you're going to see it all. So now you know how to find the IP address and the MAC address on your computer. Now, when people ask me why we don't do wireless and why it's not reliable, here's the reason. We used to have this concept in networking called the hub. And then we invented a switch 20 years ago. Now, for some of the AWS certified people, I know there's a certification provider that calls switches and hubs. They couldn't be more far apart than you can possibly imagine. A hub does this. A hub basically creates wireless. So here's what a hub does. And here's what wireless devices. You have two PCs on the same network. And they're either a hub or they have Wi-Fi cards in them. Same thing happens. Here's what happens. Computer 1 and computer 2 both try and send data at the same time. Now, what happens is because they're in a non-full duplex environment, it's like two people shouting at each other, I am here, I'm here, I'm here, I'm here. Now, if two people are screaming, can anybody hear anything? Not at all. So what ultimately happens is that wireless, and in the old hubs, which we haven't used, thankfully, for over 20 years, the two computers would talk at the same time. And then computer 2 would say, okay, I can't talk because computer 1's talking. And computer 1 would say, I can't talk until computer's talking. So they would both stop talking, and then randomly, computer 2 would say, I have to speak, and then randomly computer 1 would speak. And guess what? Hopefully that worked. Now we add 3 computers. Now we've got 3 computers. The chances of them speaking goes up together. Now we add 30 computers, all in the wireless. Now, if any one of the 30 speaks, the other 29 cannot speak at the same time. And if they do, they both collide and their data collides and they both have to restart transmitting. So that's why hubs are not reliable. And that's why wireless is not reliable, because the wireless network may say 3 gigs. But if you've got more than a couple of users, you're never going to get more than 10% of the capacity out of it because of these collisions where everybody's talking at the same time, colliding. So imagine giving a presentation with 1,000 people screaming in the same room at the same time as loud as you. Nobody's hearing you. So that's why we don't use wireless for anything that matters. Because if I'm on my phone here right now, let's say I wanted to say, okay, how many YouTube subscribers do I have? If I check this, and guess what? I can't figure it out. It doesn't matter. Wireless. Now, I have a medical application, an application where if a doctor can't open the application, they won't have access to the patient's information and somebody dies. I'm using wireless. Someone's going to die. Why is somebody going to die? Because 2 people are going to be trying to send data at the same time. Everybody's going to back up the data. We might have 50 nurses and doctors at the hospital on the same network. They're all trying to pull data. They're all talking at the same time. Everybody backs off, and nobody gets any data through. So that's why we never use wireless for things that matter. That's why we haven't used hubs in 20 years. The collisions. So if everybody was in a hub, everybody's data is going to be talking at the same time. But when you're in a switch, it's just you and your own switchboard, except for the broadcast that gets sent on every port. So we're going to talk about that. We're going to talk about broadcast domains at some point and collision domains. Not now. It'll be in the content. Now, by comparison, this is full duplex. Because it's full duplex, this person can send, and a switch can send and receive, can send at 100 megabits per second and receive at 100 megabits per second. This is great. Now, this device can send at 100 megabits and then Oh, wait, this person over here was crazy and plugged a hub into the switch. Now this is half duplex. Now, if 2 or 3 users are plugged into this hub, every time this user tries to speak and somebody else tries to speak at the same time, they're going to back off and no data is going to go through. So keep that in the back of your mind. That's what we're actually talking about. So we're going to actually start into getting some fundamentals of WANs, which is going to be really fun. And then we're going to start talking about things. So let's continue with the content. Unless anybody wants to take 20 minutes and actually get a feel for what is a Cisco router and then go back to the content. So if you'd like us to do a 15-minute lab to do a walkthrough of the router, I'm up for it before we start the next session. Let us know in the chat box below. Or if you want us to keep with the content, say keep with the architectural content and the knowledge content, and I'll do that. So let me know. You choose your own destiny, but I'm going to make sure you have a good time either way. Type lab if you want lab, type more content if you want more content.
And remember, we got a bit of a delay. So here are the responses. I'm not surprised by this.
I'm not surprised by it at all. So let me do this. We may have to reset my EVE-NG server up with OBS, but I'm not sure. So let's see if we can do it first without it. So let's do EVE-NG. It looks like most people want to do a little bit of lab. We'll do a quick lab, and then after that, we'll get back to, we'll do some questions, and then we'll get lots of content. But let's have some fun. Let's do a little bit of tech content. Okay, while we're at it, how do I do this? Okay, let me go to EVE-NG. Can you guys see it? Okay, nope. Let me go take care of this. Properties. Okay, woohoo, we got it. Okay, so let's do a nice little lab. Let's just walk into this. We'll call it Cisco router.
Can you make your window, your browser window bigger?
Yes. Okay, so here's what we're going to do. And if any of you guys ever wanted to do a real network simulation, there's, Cisco has a viral program, and there's EVE-NG. So you can buy a rack of Cisco routers, and that's great. Or you can set up an EVE-NG server. This is a professional EVE-NG server. You can replicate cloud environments with it. You can replicate routers, switches, firewalls, etc. So in this case, we're just going to create a Cisco router, and we're going to go play with it. I'm going to walk you through some basic intro to the router. So,
and Mike, before you get started, I want to let everybody know we can't zoom to make text bigger on this. We can zoom in to make the diagram bigger, but we can't. There's going to be pieces where there's text windows because of the nature of this program. We can't zoom in on text in those specific windows. So we recommend that you go full screen if you're on YouTube.
Absolutely. And letting you all know, EVE-NG is used by every major company right now to test and run simulations. So we're using the most common, most industrial grade thing you can find. So we've created a device. We're going to turn on the device. Now, when you boot up a router, if you're connected to what's called the console port, and we'll get to that, what you're going to see is it's going to turn on like this. You're going to see it boot up. And what happens is there's some flash memory. And on the flash memory, what you're going to find is it's going to have an operating system, and it also has a type of RAM where it'll have your configuration. But this is a brand new router. So it's going to boot. It's going to take longer than I wanted to, which is going to be annoying. It's going to read us all of our copyright information. It's going to tell us about the cards that are in the router. And we should be pretty close to it being booted up. We're going to do lots of router stuff this week. I will tell you, the person asked CCNA versus AWS Certified Solution Architect Associate. The AWS Certified Solution Architect Professional doesn't hold a candle to what's inside the CCNA. The CCNA is about 4 times deeper than the AWS Certified Solutions Architect Professional. To put it into context compared to we're using this, not packet tracer, because we're using a bigger, more industrial solution, not one that's more of a temporary thing. So when these routers come up, here's what you're going to have. You're going to have it say, do you want to enter the initial configuration dialog? This initial configuration dialog that you're using is, guess what? 30 years old. It was an auto questionnaire. What do we know about auto anything in technology? It will destroy anything you have. Auto anything is bad. So we're never going to use auto. So it asks if you want to use auto configuration. And for, guess what? 30 years, Cisco has taught people not to use this. Because auto is good until it doesn't work. So now your systems come up. Now it's giving us some information. It's telling us about the type of cryptography that's installed on this. And pretty much we're rare. So when you get to the router, you're going to see something. This is a brand new bank router. It says router. They come out of the factory like this. And yes, those messages you see on the screen like that, that's called the syslog messages. And these routers will be spewing these messages constantly. And we'll have thousands of devices all sending off logs. So we collect logs. Logs tell us a lot. So if we want to do anything with these routers, we have to go from what's called user mode to privileged executive mode. I didn't make up the term. That's also called enable mode. How do we get to enable mode? We type enable or en, but I'm going to use the full word. Now look, kind of like on a Unix system. Note how you go from this greater than prompt to this hashtag prompt or the number prompt. That means you're in enable mode. So now I can do things. I can look at the configuration of this, show running config or show run. You can see certain things that are here. It tells me the version. It tells me the current host name of the router. It's going to tell me the type of switching it's using. It's using Ceph. It's telling you the IP addresses, the speed and the duplex of these things. So, for example, if I want to change the name of the router, if I want to configure the router, I type config, and we type terminal, but org t. So now note it says router/configuration. So let's think about this. Every device we're going to put a management address. So, but let's give it a name. If the device says router, we're not going to know what it means, right? Imagine just having, I work on networks that have 10,000 of these things. Imagine not having a name. So let's just say host name. Let's make it simple. Let's call it router 1. That's what they would do in a CCIE exam. And I probably didn't spell it right. Okay, I didn't. Okay, now it says R1. Notice it says R1 instead of this. Okay, now what if we were to put a name, put a management port on this? Let's say we call that a loopback address. And we'll talk more. We'd create an interface, and then we give it an IP address. Let's say 1.1.1.1. And then it's going to need a subnet mask, 255.255.255.255. We'll go heavily into subnetting. Don't worry. I forgot to type the words address. So ADDR is enough. We'll turn on the interface, no shot. And poof, now you'll be able to see if we do a show IP interfaces on this router. That's going to give us too much information. What you're going to see, I could help if I could type. You're going to see that I just created an interface called the loopback address. You can see that this is the IP address. Note, this router has 4 Ethernet ports. Note, they all say administratively down and line protocol down. So what does that mean? Well, if we look at this running configuration, look at the interface. Interface gigabit Ethernet, no IP address, shut down, duplex auto, speed auto, media type. Do you think I'm going to leave anything to auto in reality? No. What am I going to do? I'm going to manually do this. So I'm going to type config t. I'm going to give it an IP address. Let's come up with 172.16.1.1. Let's give it a /30-bit mask because that's what we typically use on a WAN link. And we're going to be explaining what all this means. I just wanted to give you guys a little bit of a lab to give you a little bit of a breakup.
Hey, you said 172 and typed 127.
Thank you.
And now you typed 170. There we go.
So the reality is when you're ever going to work on networking, you're going to build your configuration in Notepad ahead of time, so you don't make configuration errors like I just did by typing. Oh, what am I doing? Maybe I have to type ADDR. Oh, we're not in the interface. Int G0/0. Now we're in the. Then we'll put that same IP address, IP ADDR. We can do 172.16.0 or .1.1, 255.255.255.252. And if I turn this port on and I do a no shut, do we think the port's going to come up? It'll administratively come up, but is it going to come up? If your Ethernet card is not plugged into the wall, do you have any link light on your card? No. So let's watch how it happens. And I'll show you the benefit of a keep alive, and we'll get back to the content. So as soon as I do this, interface gigabit Ethernet change to down. Down. Why is it down? Why is it down? Now this is kind of weird. Oh, I didn't turn it on. I did a no shut, but why is it down? Even though I manually turned it down, why is it down? So guess what happens? If you plug in your switch, your router, and it's not plugged into anything, you've got two choices. We could do one of the following. We could disable the keep alive and keep it up, or we can plug it into a switch. So you know how we talk about health checks for you cloud computing people, and we talk about DNS saying, "Are you there? Are you there? Are you there?" And then the servers respond, the sites respond with, "Yes, I'm here." And DNS forwards the traffic. And we have load balancers that have 5 servers behind a load balancer, and they run a health check. "Are you there? Are you there? Are you there?" And they respond, "I'm here, I'm here, I'm here." And if they don't respond, "I'm here," they get removed from the rotation. So we plugged it into Ethernet, and Ethernet's sending a keep alive. "Are you there? Are you there? Are you there?" But there's nothing to respond. So that's why it says up, down. So we've got two options. Now, to just show you, to argue the point, we could go to interface G0/0. I can disable the health check by typing no keep. Now watch what's going to happen to this port now. Show IP int brief. It probably will, it may go up. It may not. But I can show you what will make it go up. We're going to plug a cable into it. Verify. Okay. Cisco got a little smarter. They used to let us on our lab exams type no keep alive, which was the most dangerous thing you could do. But it used to work for exams. But they disabled it in this feature. So let's do this. And let's re-enable the keep alive, because that's kind of bad practice to do this. So keep. Okay, so now let's fix this. Why isn't it going up if the cable's not plugged into anything? So let's now add an object. Let's add a node. Let's add a switch. While we're at it, we've got a nice switch here. Let's turn the switch on. Router to switch, straight through cable or crossover cable? Everybody type it in the chat box. Router to switch, straight through cable or crossover cable, while we're waiting for the switch to boost. Switch is booting. As we mentioned, we can't change the size of the display. For the commands, we recommend that you maximize the size of your window. Ruth, router to router, crossover. Switch to switch, crossover. Router to switch, straight through.
Can you repeat those two again, Mike?
Router to router, crossover. Computer to computer, crossover. Switch to switch, crossover. Router to switch, straight. Host to switch, straight. Switch to router, straight. So pretty much you use a straight cable anytime you plug one device into another device, except for you use a crossover if you're going to plug devices into each other without a switch or a network device. Okay, so now we're here. Switch is up. Let's enable this. Okay, now what's going to happen if we actually create a port, if we plug in a wire between these two switches. Let's do it. Let's plug in a physical wire between here and here. Now let's do gigabit 00 on the Cisco side, on the switch side. Now let's see what happens to our router after this. Oh, look at that, automatically. Do you see this thing on the port? Interface gigabit Ethernet changed to up. Line protocol changed to up. So before, this is what we looked like here. Now administratively down means shut down manually. Down, down. Now if we do our show IP in brief, what are we getting now? Oh, look at that. It's up, up, up. Pretty cool, huh? Now guess what? If we go to config T, int, this switch may require us to make a VLAN or it may not. Let's see if we can just put an IP address on the port. Yeah, we can't. This is a layer 2 switch where we've got to create interface VLANs. But some let you do it and some don't. But that's all we wanted to show you. I wanted to show you there's this. Now you got a router, but let's look at this configuration a little more. That's a switch. Let's go back to the router. They do things differently. Run. So we could turn this device into a web server if we wanted. We wouldn't want to do that, but they have the ability to manage it. We can manage the line console. We can dial in via an auxiliary line, which we'll talk about. Yes, EVENG requires a license, and I bought the professional license. It's the most robust simulation package in the world. And that's why we use it, because it works for cloud architects, network architects, incredible software. Oh, Alto firewalls, Juniper firewalls, networks, all the stuff you can run through here. So kind of keep that in the back of your mind. That's the first mini lab we're going to do. We're going to do a lot more. We're going to be connecting things. We're going to be showing you packets flowing through the network. But I want you to at least get a feel for the router, see a little bit about what it is before we get into more content, because I just wanted it to be a little bit fun. So covered a lot of stuff. We're getting ready to talk about the next section. So, let me know if there's any questions.
There was a couple that I don't think you got to. I'm going to look back at them just to make sure.
And, well, I can see one thing. People are looking at simulators. Look, GNS3 is a fine simulator. Cisco's got a packet tracer, which is fine. But none of them hold the candle to the professional version of the EVENG. But not everybody has big needs. For the CCNA, you can use the Boson practice thing, but it's like $200. You could use GN3, GNS3 if you've. Any of them are possible. I use the most redundant, the most sophisticated kind because we run a global training organization for cloud computing. And what you can do when these things come up is what we all do is what's the difference between link up and down versus line protocol? Well, typically speaking, there's the link up and down, which is like, layer 1. Is there a cable plugged into it? And then there's the line protocol, which is typically layer 2. Is the Delcy up and running in frame relay? Is the Ethernet frame is an Ethernet port? That's really what we're talking about. Layer 1 and layer 2. Good question there, Anthony. What do I think about 802.1ax? I'm pretty sure that's wireless, but I don't think in terms of acronyms. Let me just confirm 802.11ax is wireless, since 802.11 is generally wireless. Yeah, it is. That's Wi-Fi 6. Again, Wi-Fi 6 is non-reliable, so it's used for things that are not critical, such as playing video games, or trying to check your social media. That's what Wi-Fi 6 is good for. Anything that matters should never be plugged into wireless, because it's going back to the collision nightmare that I was describing to you. Well, NitroPan, we don't normally manually configure our routers. We typically take a router config, make it in Notepad, and then we cut and paste it in. But we could set up a TFTP server and pull our startup pull a running config from the TFTP server and save it to memory. Yes, we could. I've done it lots of times, but typically what we do is this following. We keep it in a Notepad file, and that's it, a text file. In fact, NitroPan, here's how we used to back up networks that would have 5,000 switches. We would have some Unix Linux person write an expect TCL / script that would basically log into every router and copy the running config to a TFTP server, and then we'd have text files for all of our routers. And that way, if we had to replace the router, we would just cut and paste the new config in. So yes, we do automate it. Exactly. Okay, hold on. No, Chris. And then go to the next one, Chris. Okay, Evelyn, great question. So whenever you configure something, always check the documentation and make sure there's not errors. Now, I've been doing this forever. So here's the thing, Evelyn, because boy, Evelyn, that is a really great question. Let's go back into this router. Let me share this for a second, because what a great question that is. So let me do a show IP interfaces. We can look at the interfaces. So we've got a gigabit Ethernet 00, 01, 02, and 03. So let's try and do something wrong. Config T. Let me try to configure an IP address or an interface gigabit Ethernet 0/4, which doesn't exist. Int GE or G0/4. This doesn't exist. Input error detected. Okay, well, let me try. Let's go to the right one. Let's go 03. Now let's try and put an IP address that's not right. So let's do an IP ADDR 172.16.0.0 255.255.255. Now, this .0 for this subnet is the network address. Let's see if it takes it. Incomplete command. What's it want? It won't give it to me. Why? Because the IP address is invalid. Now, if I were to change it to a valid IP address, now it takes it. So what you're seeing, and I love that question, and the reason I brought it is for the most part, the routers won't let you make a mistake, and they catch you when you're making these errors. So as a rule, you don't have to worry about it, because they'll catch you along the way, and they'll say, nope, that doesn't work. Nope, that doesn't work either. So that's why we're really talking about it. It's hard to make a routing configuration error. Now you can if you can have 10 ports and put the wrong addresses on each port, and then you've got a nightmare to go troubleshoot, but it almost doesn't let you. So let you know, I always build the configuration ahead of time and paste it in, and that way I don't make spelling errors. But I'm doing this stuff live with you. It's live. You never know what happens on live, and that's part of the fun of live. Your computer can freeze up, and we can have fun. So let's get back to some content, everybody. Okay, so, the first day we've got a lot of academic stuff, which is not my favorite kind of thing, but we have to talk about it. So let's talk a little bit about some of these technology architectures. We're going to talk about lease lines, Ethernet is a WAN technology, and we'll talk a little bit about internet access. And this is really an intro to the content, but we've got to start somewhere. In many parts of the world, you're still going to be running WANs like this. What's it going to look like? You're going to have a campus or an office where you've got a switch and a router, and you've got another office and a switch and a router. And we're going to connect these things over a WAN link. Now, traditional WAN technologies use serial lines or optical lines. T1, E1, T3, E3. ISDN is still being used in parts of the world. Frame relay is still being used in China, for example. I know some people that have worked on it recently. So lots of these old school WAN technologies still exist. Now, for the most part, in the US and the UK and Canada, we're using Ethernet. But for most of the world, we have serial lines. This is old traditional technology, which is slow, but highly reliable. And you're going to see it throughout phone systems throughout the world. Now let's talk about how we buy stuff. So for example, we might have one building in New York and another building in San Francisco. And we've got a router with a private line between them. Guess what? That's how they communicate. This has been going on now for 30, 40 years. Routing in between subnets, 30, 40 years. Not new. So let's talk about, traditionally speaking, like a metro environment. You've got a site that connects to the telco switch, which then plugs into another telco switch, which goes to the next customer site, and all the wiring is underground. So, there's two kinds of connections. There's private connections, which you buy from site 1 to site 2, private connections. And then guess what? There's non-private connections or public connections that use the internet. So when you connect to the internet, that's connecting to the internet. But a private line is for me to buy a link directly to Chris's house in the Tampa area from my house in the Palm Beach area. Direct link. No one can see it. 100% secure. 100% secure. And 100% of the bandwidth is mine, and the delay and the jitter is guaranteed. So how good do we feel about that as far as knowing that our content gets to where it needs to be? It should be pretty darn good. So keep that in the back of your mind. So metro environment. So as we were discussing, and bear with me for a second, whenever we're dealing with communication from one layer to another layer, we've got that data link layer, right? Now remember, with Ethernet, what's that thing that's at the data link layer? A MAC address. What does Ethernet encapsulation look like? Ethernet encapsulation look like. But when we're dealing with WAN lines, unless the WAN line is Ethernet, it's going to use another form of encapsulation, another form of encoding and decoding the messages. So I want you to think of it this way. I saw Alex's name on the call, and he said Kalimata, which means good morning. If I had responded, if I got that message from Alex in the morning, I'd say Kalimata, Alex Dikanis, which means good morning, Alex. How are you today? And he would respond Imapoli Kala, because I'd be speaking Greek to him. Why? Because he's Greek, so I would use the Greek language. So when we're dealing with Ethernet, we're using the Ethernet language. Now, if I called Pierre in Canada, I'd call him in French because he's in the French part of Canada. So if I had a WAN link to him, I would use his natural language, which was French. And Leo, who speaks fluent English, Portuguese, and Spanish, if I wanted to communicate to him in the language, I would use the language of his choice. So what are we dealing with in networking? We're dealing with choosing an encapsulation type for the WAN type. So when we're dealing with WANs, we've got two types of framing type, two types of encapsulation. We can use point-to-point protocol, or we can use something called HDLC, which is the standard protocol that's used on Cisco routers. So what is this stuff we're talking about? What's it going to look like? Well, it looks like anything else where everybody has a header that they create. Now, I don't like to use Cisco proprietary anything. I love Cisco. I think it's the best company in the world to work for in the world. They've treated me great, but Cisco HDLC is Cisco proprietary. So I would probably use a traditional protocol like point-to-point protocol because I always use open standards. But this is a fantastic protocol. It's in use all over the world. And Cisco is the majority of the network. So keep that in the back of your mind. And the framing looks like this. You've got a field, an address, a control, a type, and a variable, and a frame check sequence. Just like everything else, it's all the same in every language that we're talking about. That's what we do. So let's think about this. What's it going to look like and how do routers work? So let's go back to the routing table. We're going to walk through this routing time thing. Let me tell you, 30, 40 times before we ever get to the routing on the routers, because I want you to know it. So let's go back to the routing thing. Let's go over here and let's imagine PC1 wants to talk to PC2. PC1 says, I want to talk. PC1, sitting on PC1 is Cindy the cat. She's licking her lips, cleaning her hair. She's happy and she wants to reach her her aunt, Sunny the cat over there in Tampa. So what does she do? She gets on my computer, and Cindy loves playing with her computer. And she gets on the computer and she goes to www.sunnythecat.com because they've got some kind of cool messaging application between them. They talk all the time. So Cindy goes to that computer and she says, wait, I want to go to sunnythecat.com. So the first thing she does is say, do I have a route? And she says, no. And then she says, do I have a default route? Which says, if I don't know where to go somewhere. And then she says, I do. Good news. It's router 1. And then she says, who has the MAC address to Cindy? And PC1 does this broadcast. It's called an ARP broadcast. And if you get a sniff route, it'll say, ARP, who has the MAC address for this? And the router will answer, I have the MAC address for Sunny the cat. So the PC sends the data to router 1. Now when it gets to router 1 says, do I have a route on the routing table to get to PC2 or Sunny the cat? And it says, guess what? I know how to read Sunny the cat. Go out my right arm to router 2. That's how you reach Sunny the cat. So next thing router 1 says, who has the MAC address for Sunny the cat? And router 2 responds, use my MAC address. I will proxy ARP. I will respond. So now the data is at router 2. The data is at router 2. And that router 2 says, do I have a route to sunnythecat.com? And it says, yes, I do. It's directly connected to my Ethernet port. So then it says, ARP, who has the MAC address of sunnythecat.com? And PC2 responds, ARP, I have the MAC address. So PC2 now gets the message because it responded. Now PC2 says, oh my God, that's my beautiful friend Cindy. Cindy wants to tell me about the new squirrel and rat that she caught last night, which drove her daddy, Mike, unhappy because he had to clean up the mess. So PC2, which is Sunny the cat, says, okay, I want to talk to you, Cindy. Now, do I have a route on my routing table to reach Cindy the cat? And guess what? It doesn't. So it says, do I have a default route, which says if I don't know where to go? Yes. ARP, who has the MAC address of sunnythecat.com? Router 2 says, I have that MAC address. I'm the proxy ARP. Come to me. So PC2 sends its device to the router. Now, the packet's at the router. The router says, who has the MAC address? Do I have a route for Cindy the cat? And it says, yes. My left arm goes this way. But wait, I have an Ethernet connection. ARP, who has the MAC address of router of Cindy? Router 1 says, I have it. I replied to the ARP. Now, packet's now on router 1. Router 1 says, do I have a route on my routing table to Cindy the cat? And it says, I know where Cindy lives. She's over here, but I don't know her MAC address. ARP, who has the MAC address to Cindy the cat? Cindy says, I do. Purr, purr, purr. Now the two of them are communicating like this. And every part of that communication is going to go back and forth. The routers are going to forward it based upon the next hop, and it's going to come back via the next hop. And that is how routing works. So you got the layer 2 with the ARP, and you got the layer 3 with the networking. So that's what we deal with in networking. It's pretty much just that. It's all that. So let's talk a little bit about encapsulation and decapsulation. Again, I'm going through so much fundamentals over here to make sure you're prepared for what comes next. So here we've got a PC. We've got an Ethernet frame, right? And you can see it. 802.3, that's your Ethernet frame, that's your IP packet. So it goes to the switch. Now it goes to the router. The router pulls that Ethernet frame on. Why? Because it's no longer Ethernet. And it sticks the HDLC. So remember, I talked about Alex. I initially called him, and he's in his restaurant. The person answers the restaurant, picks up the phone, speaks in English, and I say, I'd like to speak to Alex. Alexandros picks up on the phone and I say, Kalispera, Dikanis, which is good afternoon. How are you today? So I change the encapsulation because I'm using a different media. Now we get across the WAN link. Alex and I are talking Greek. Now Alex hands it off to somebody else. And it's Ethernet, so I speak Ethernet to him. So that's how that works. So encapsulation, de-encapsulation. Now, guess what? Now we're entering the cloud. Do you know what a cloud really means? I'm going to tell you what a cloud really means. What the cloud really means is follows. It's all hidden and you don't know what it is. That's what a cloud means. That's why in Frameweaver we use the cloud, and ATM we use the cloud, the internet you use the cloud, because you can't see which autonomous systems are talking to each other as the average user. You just know you connect to it and it works. So now we've got two kinds of options. We can connect to a WAN service provider. And what do you think this can be? They can just create us a wire across their switches and everything's perfect. We get a fiber optic connection to them and they run a connection back to their switches. What do you think a direct connection is like? Or an Azure Express Connect? It's this. It's identically this. You're buying basically a WAN service. That's it. Now, what if we decided to take this WAN service, which is traditional wire, and what if we decided to create a different kind of network? We created an IP network, and then we added something called RSVP signaling, some MPLS, or tag and label distribution switch software, and we created an MPLS network. And what if we took a wire and all of the wire's electrical signals and tunneled them over an MPLS network? And we'd create a pseudo wire or a wire of nothing. Hey, when you go to the cloud and they create you a VPC and it's your logically isolated data center out of nothing, it's the same thing. It's the same logical connection, which is why cloud technologies are 40 plus years old. It's not new. I know AWS will say brand new feature in 2021, east-west routing or routing between subnets. Cisco did the same thing 40 years ago. So all the cloud stuff is 30 to 40 years old. So if you know the network, you'll know the cloud. So that's all Ethernet over MPLS is. It's just a wire. So what does it look like? You're sending a packet over here. This guy or girl or whatever you want to call the user over here is sending a packet over here. And it just gets pushed through a wire. No big deal. There's nothing fancy to it. So now you know what's going on in these networks. It's not that complicated. It's kind of like the hot potato routing, meaning, and I'll show you one more time, hot potato routing. Okay, so let's look in this thing. This system over here wants to reach this system. So what does it do? It looks in its routing table. Do I have a route? And it doesn't. So it goes to router 1. And router 1 then looks in its routing table. Do I have a route to 150.4.0? Yes, I do. Go out this port. Gets to router 2. Do I have a route to this destination? Yes, I do. Go out this port. Ethernet over MPLS. Fine. Packet gets here. Do I have a route to this? Wait. Interface G00, next hop not applicable. That means directly connected on the device. ARPU has the MAC address to PC2. I have the MAC address to PC2. PC2 responds, sends his data to router 3, which goes to router 2, which goes to router 1. That's it. That simple. So let's talk a little bit about what goes into the IP headers, because we're going to need this. There's a version. What version of TCP/IP? There's a length. How many bytes? There's this DS field. This DS field is really important. It's the type of service. So I can set this to critical. I can set this to low priority. Now, if I've got a network that's aware of QoS things and is looking for the degree of service field, I can then say, voice and video go first, and Cindy the cat's download of cat photos from the internet goes last. Now, if I deprioritize Cindy the cat's cat photos, my cat won't be sleeping on my chest and licking me to wake me up at 7 o'clock in the morning because she'll be mad at me. But the point is she can't make sure that our YouTube thing goes down because she's downloading 50 terabytes of data on cat photos. So that's kind of thing. So we can prioritize, and we will get heavily into QoS because QoS is critical for security. Yes, QoS and security, and the two most people don't realize it, but all experienced network architects know that you can use QoS to dramatically increase the security of your situation. So, time to live. Okay, so someone asked previously, hey, we send packets out there, what happens to them? So every time a packet hits a router, its time to live gets degraded. So all packets have a time to live. And what is that time to live? How many routers they'll go through before they die. And why is it there? Because if we had a loop and I sent a packet and it circled the internet 1,000,001 times and never died, I could fill up the whole internet. So what happens is the internet has the time to live. Let's say I want to go to Ivadoikio, and there's 20 routers on the way to Ivadoikio's house. So I go to the first router, my TTL is 20, it's now 19. Drops it to the second router, my TTL becomes 18. Drops it to the third router, my TTL becomes 17. Once I cross 20 routers, my packet is dead. So the application will set a time to live based upon how far you think it needs to be. So I know we're hitting all the fundamental concepts right now, but we just have to. We'll get to the fun soon. I promise it's coming. Let's not waste your time. Let's go back to this. I'd like to show you the ARP process again. So when I said router 3, it literally looks like this. ARP, who has the MAC address? So what happens is these devices send broadcasts. Now, what is a broadcast? A broadcast is when you send something and everybody has to look at it. That's what a broadcast is. When you send something and everyone has to see it. That's what a broadcast is. So I want you to think about this truly. If you have 500 devices on a network, what are the chances that all 500 of these devices at the same time are going to send devices? A lot. So, allergies are there. So what happens is every device you have sends a broadcast. So at some point we'll talk about subnet size, and we'll say your subnet should never go above a /24, /23 at the largest because of all this broadcast. This is one of these broadcasts that we're talking about. Every time somebody sends a broadcast, every host on the LAN has to look at that broadcast and process it so it can degrade the performance of your system. So we'll talk much more about that later and why. So the good news is the next section we get to do some lab stuff. So before we get to the next section, let's open it up for some questions and let's have some fun. Chris, I'll let you aggregate some questions. I saw a lot of stuff coming in. Where does PC1 get its MAC address? PC1 has its MAC address and it's physically burned into the card. So let's see if I can do this. Chris, I'm going to try and share another window in OBS. I don't exactly know if I can do this. Okay, I can't do this. Okay, so totally fine. If you do an IP config on your computer, it's going to be very simple. You're going to see the MAC address that's attached to your computer. Now, when everybody do an IP config, /all if you're on a Windows system, and if you're a Linux system, do IF config, pull that up in the chat box. Note, you're going to see your port and you're going to see the MAC address. It's burned in. It's called the MAC address. So my MAC address is Foxtrot Charlie 34 Niner 7 Alpha 0 Foxtrot Delta -16. Now, when we look, and if any of you guys pull up that IF config in Linux or IP config /all, and you're looking at your MAC address, you're going to notice that it's got six things that are each like FC-34-97. Now, if you look at the first half of that, the first three, mine is Foxtrot Charlie 3-4 Niner 7. That's something that's called the OUI. And that basically identifies who the MAC address manufacturer is of your product. And if you do that, you will see whether your card was made by Intel, whether your card was made by, for example, Broadcom, etc. You'll see it. And then the second half of that MAC address, the last three dashes, that will be the address that's specific to your card. First part called the OUI. Second part is called is a unique address to your card. And remember, this is in hex. So with binary is 0 and 1, hex is 0 to F Foxtrot. With 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, alpha equals 10, bravo equals 11, Charlie equals 12, delta equals 13, echo equals 14, and Foxtrot equals 15. Chris, you can bring in the next one. Well, ARP is a hybrid layer 2/3 protocol that maps a layer 3 IP address to a layer 2 MAC address. So routers communicate to other routers via ARP, and it's because at layer 2 if they're using Ethernet connections, but they still communicate via IP. See, where does PC1 get from its MAC addresses from all the other PCs it wants to talk to? Well, if they're on a subnet, ARP everybody, yoo-hoo, all of you, who has the MAC address? And then somebody responds. That's what it's really like. Yoo-hoo, everybody, I'm out there, who's got this? If you're on a LAN. Now, if you get off of your LAN, Sadie, and this is where it gets tricky, off of your LAN, the router responds to that ARP. So going back to this example that I described to you over here, when we're in this, let's pick up one of these, let's go to one of these routers because we walked through this, but that's a good question. So let's go back over here. PC1 says, who has them, it looks in its routing table and it sees router 1 has the route to PC2. So PC1 says, ARP, everybody out there, who has the MAC address for sunnythecat.com/PC2? Now, do broadcasts get forwarded outside of a subnet? No. That's why we use routers, to make sure the broadcasts don't leave the subnet. Routers promote security, all kinds of cool stuff. So we'd have a problem. If PC1 says, yoo-hoo, everybody, who has the MAC address for PC2? PC2 can't answer because the broadcast from PC1 will never make it to PC2 because the router stops the broadcast at R1. Routers stop broadcast. That's why they're so awesome. So what happens is when PC1 says, ARP, who has the MAC address? Router 1 says, I do. And router 1 answers on behalf of PC2, and that's why it's called proxy ARP. Router 1 says, I have the MAC address. So when router 1 sends the data to router 2 says, ARP, who has the MAC address? So we're always going to be transferring things as we go through a network. So I hope I answered your question there, because that was an exceptionally good question. Well, does router 2 have an Ethernet header trailer instead of HDLC? If it's got an HDLC link, it'll be HDLC. But once we get to the Ethernet port, we're going to strip off that HDLC, and we're going to be communicating to the routers via Ethernet. So it's going to have to swap. That's what we do. We encapsulate. So layer 2 Ethernet. Now we're going to WAN links. Strip off the Ethernet header, smack on an HDLC header. Go back out the Ethernet port, pull off that HDLC header, slap on an Ethernet header. It's going back to communicating in the right language of the people you're speaking to at the same time. That's really the key. Nice question there. Is the time to live the same thing? No. So what happens is we will be doing trace routes, Alex, and the trace route will literally show us the path that we're going through the network. And then I will show you how, when your traffic gets lost on the network, to use the trace route to solve it. That's coming up in the troubleshooting sections. Definitely. Great question. What methods do you use to configure switches? Generally speaking, when they first come out of the box, you have to connect to the serial port to set them up and put an IP address. And then after that, you can use Telnet or SSH. We used to use Telnet. We don't really use it a lot of the time anymore because it's plain text and hence not secure. So we tend to use SSH. We can now push configs via an API in today's world, if we choose to, once they have an IP address on them. But we also, the routers typically have an auxiliary port as well. And you can basically plug in a modem to them. And we can call it up and, ding, 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 ding. And it's an analog line, which we had set up to 9,600 bits per second, 8 and 1, which we'll talk about that later. and we could basically dial a direct phone number into it, which is highly secure. So these days we're predominantly using SSH because it's somewhat secure compared to Telnet. It's not the most secure protocol in the world, but it's secure enough. Does multicast addressing use broadcast? No, multicast addressing uses multicasts, which are a very specific kind of thing. And broadcasts aren't forwarded out of the thing, but with multicast we can. We create something called reverse path trees to the source. I actually consulted as an IP multicast engineer for about 5 years, so I've spent lots of time in IP multicast, but reality is multicast can get really complicated, and I wouldn't have enough time in the next 2 weeks at 8 hours a day to really cover multicast if we spend 8 hours a day for 2 weeks straight. So because of that, I'm going to just say that multicast is a special kind of broadcast. For example, if you have TV in your house and you have IPTV from your cable company, it's multicast. And what multicast is, you subscribe to what you want and you see whatever you want. But if somebody else doesn't subscribe to it. So there's this new TV show I watched the other night. It was called, it was about money laundering. It was called Ozarks. It was on Netflix. It was pretty good. So here's the key. If that was being streamed and 1,000 people tuned in at the same time, because it was live streamed, guess what? That would be multicast. And that way, the server would send it once and hundreds of thousands of people could watch it as live TV at the same time. That's versus me watching it at my own time, which is unicast. So multicast is like that, but that's kind of where it works. Chris, I think we can do one more. Alex, I'm glad we got your question. Does ARP work with CDP? So Franklin D, I strongly recommend if you want a career in architecture, never, ever, ever to use acronyms, because CDP can be a lot of things. It could be a coupon code. It could be Cisco Discovery Protocol. I could give you at least 50 more things than that is. So my recommendation with regards to technical precision is never to use acronyms. If you want to be an architect and use an acronym, that basically will keep you from being hired, because the hiring manager won't hire you. For engineering, it's acceptable. So keep that in the back of your mind. ARP is mapping a MAC address to an IP address, and CDP, or Cisco Discovery Protocol, assuming that's the CDP you're talking about and not like something else. CDP helps routers identify other routers, so they're completely unrelated. When a packet is sent from router 1 to router 2, what's the packet's destination? It is directly the IP address of the next router and the MAC address of the next router. The ARP is to figure out who has the MAC address, and then you send it. Chris, where were we on questions? Do we have to get back to content?
No, that's it. We can get back to the content.
Okay, perfect. So let's get back to the content. Let's have some fun and talk some networking. Let's make sure we get you to the right section. Okay, so in this section, guess what? It's talking about using the command line interface. So we're going to do some of that. So, this goes back to the last question, which was super intelligent with regards to how do you manage these? And I love the question. So what happens is, in the old days, our computers had a serial port. And we would plug the serial port. It had like a bunch of wires, and we'd plug it in. And what would happen is we would take the serial port. The serial port would give us something called a rolled cable. We would plug the cable from the console port into the serial port of our PC. Now, in recent years, PCs stopped making serial ports. So what did we do? We bought a USB serial port that would plug in to emulate the serial ports. And that's how we would connect to these things. And that would give us hands-on terminal access. And realistically speaking, that's what I'm referring to over here. This is what I'm referring to. There's some devices that have a USB thing that you can, that's the converter that you would use to the serial port that I was referring to. And that's pretty much it. So let's talk about setting up. a terminal. So on your computer, you're going to have to set up the terminal settings, and here's what they need to be. I'm going to sound the alert. Test question, test question, test question, test question. Know how to do the job question, know how to do the job question. Critical, critical, critical. Learn this. These are your terminal settings. The bit rate or the baud rate is 9600. The data bits are 8. The parity is none, and the stop bits are 1. So memorize this. 9600, 8 and 1. 9600, 8 and 1. You will be tested on this, and you will need to know this for the job. You will need to know this for the job. So let's go back to the concept. 9600, 8 and 1. So when we get to these devices, we've got two sets of users. Basic, which is user mode, and enable mode, which I called privileged executive mode, because that's technically what it's called. But the rest of us call it enable modes versus user modes. So what's that look like? Well, it's going to look like this. Let's go back to this. Let's go back to this router. We get into the router. What's it look like? User mode. So Prince, it's going to be 96008N1. 9600, 8. N is in November, and the physical number 1, and you'll be good to go. So we now get to the router. We're in user mode. User mode. User. How do we know we're in user mode? It's got a greater than symbol. User mode. Type enable. It changes to a prompt, a hashtag. Guess what? That's called enable mode. That's all you needed to know. Now let me show you the difference while we're at it. Let's go back to, let's exit out of this. Let's go to the console port. We'll be in user mode. Let's reload the router.
Are you sharing your screen, Mike? Or do you mean to be?
I was trying to, but reload. Guess what? It didn't accept it. The command wasn't recognized. So now what's it trying to do? It's trying to resolve it. Hey, to telnet into this device because we didn't tell it. And it's going to time out in a couple seconds. Why can't we reload this router? We don't have the privilege. Why don't we have the privilege? We're not in enabled mode. Now, let me just take the config. Now let me type enable. Let me save the current configuration. Now this is like root access. Now let me type reload. Confirm. Yes. See the difference? Privilege comes in. There you go. We rebooted the router, but I couldn't reboot it in user mode. I could do it in enable mode or privileged executive mode. So does that sound like Unix permissions for everybody? It's the same. So when we're going through the software, as soon as this comes up, let's play with it a little bit. Let's give you an example of how to navigate this when you don't know. Now, when you don't know, what do? www.cisco.com. They give you the documentation. Heck, the knowledge required for these things is so great that on the CCNA exam, they used to give you the CD, and it still had a 97% failure rate at the time. They would give you the instruction manuals for configuration because they knew that anybody could configure anything. It was the knowledge that was hard to know on how to do it. So let's go back to this. Let's go back to this environment. Our device is going to be booted up. Okay, now, want to know what to do? There's a question mark. Wait. Gives you help. And we can look through more and more and more, one at a time. These are all the things we can do from when we're here. A lot of things. If we don't know, let's get some help. Let's type ping. Hey, we can, what kind of ping do we want to run? Do we want to run the CLNS echo, like from, which we now use with the intermediate system protocol? Are we using DECnet from 30 years ago? Is it an Ethernet frame? Is it MPLS? What kind of ping do we want to send? And we can help that. Let's say we want to configure an interface or just configure the router. What do we have here? Oh, wait, we've got new things. AAA. Wait, authentication, authorization, accounting. Where have I ever heard that term before? Cloud, they call it identity and access management. Same thing. Access list. I can create an access list. In AWS, they call it a NACL. Same concept. Azure calls it I think in Azure Network Access Control. I'm drawing a blank right now, but I normally would, it's in the back of my mind. So, that's the thing, is we can do it. So let's just, somebody else asked the question. We're now into G0/1 at support. Now you got to spell it wrong. If you spell it wrong, it won't let you. So now what do we have in options? Okay, I can configure things on the port. I can configure an IP. If I do IP, what's next? I can do an address group to tie an access list. I can pop an address. Okay, let's pop in an address. So let's do over this. Let's type in ADDR. Now what options do I have? I can tell it to pull via DHCP, which I would never do. I can come up with a pool that I could use if I was going to turn this into a DHCP server. Or guess what? I could just give it an address. 192.168.1.1. Guess what? Oh, wait, I need a subnet mask. 255.255.255.252. Wait, is there anything else I should do? I can add a secondary address. You know what a secondary address is? I can have a primary address and a temporary address if I'm changing my IP addresses, or I can just be done with it. No, I'm going to do a shut, but no AAA, meaning no identity and access management, no ARP, no backup, or I can just shut. I can turn on the interface, no shut. So the point is you're guided no matter what you do by this. So keep this in there. Azure has network security groups, but they also have network ACLs, I believe, in addition as well. So that's really what we're talking about. So keep that in the back of your mind. With every command, you can get help. So let's talk about some other things. Any of you guys or girls ever use Linux and Unix in your life? Okay, so let's do this. Config T. Let's go to interface G0/1. Okay, wait, does anybody notice that I didn't type it right? So in Unix, if I type Control A, it begins me to the beginning of the line. If I type Control E, it takes me to the end of the line. If I type Control B, typically moves me back a space. Where do you think these things come from that the command line follows in Cisco? Unix. So all of the same commands that work in Linux and Unix, especially in Bash, are pretty much the same way the Cisco command line works. Why? Where were the first networking devices? They ran on BSD Unix. Well, this is not on BSD Unix. The Juniper routers were for a while, but here's the thing. Everything comes from Unix, so that's where the stuff is coming from. So of course you can backspace on these devices, and of course you can use, the arrow keys. Also, up arrow repeats the previous commands. Down arrow will do the same thing. So keep that in the back of your mind. It's just, working your way through this, just like Linux, Unix. So if we're dealing with the switches, when we're dealing with routers, they build routing tables. And how do we see what's in the routing table on these devices? We look at the routes. So let me just show IP route. What do we see on this device? We can see the one subnet that's up says directly connected. Keep that in the back of your mind as we walk through some of these things. That's really what we're talking about. Now, if it was a switch, guess what? We'd be looking at MAC addresses. So let's kind of play with it a little more. Let's prepare this thing for Telnet or SSH, etc. So we'll go to the config terminal. Note, I typed a spelling error. It doesn't let you. So in general, when people tell you they made a networking misconfiguration and it was a typo, realize it probably wasn't a typo, because you can't make a typo. Right? It's very hard to. realize typically you can configure the wrong routing protocol. You configure the wrong routing thing. You can do all these things that are wrong, but usually it's because you didn't know what to configure, not how to configure it. Because here's the thing, we can get this configuration materials in seconds. It's easy. Just go to the Cisco page. It's knowing how to do it. So let's make this so this thing has virtual terminals that you can manage. So they're called line V2I 0 flare. Let's say here we wanted to type password Cisco, transport input all, which is going to enable us to come in via SSH, Telnet, etc. And no login. Now we'll show you what. Now we can reach this device from another one. So let's do this. Let's connect the second router. Let's get rid of this switch over here.
Hey, Mike, you're not sharing your screen.
Not sharing my screen. Yep. Thanks, Chris. Was I not sharing my screen for any of that?
It only started in like the last 30 seconds or so.
Okay, perfect. Okay, so good. So now let's delete the switch. I didn't mean to do that. So how do I remove this thing? Okay, so stop. Shut down. Let me see if I can just delete. Okay, can I? All right, we're not going to worry about that. So we're going to basically add another router. Let's say Cisco iOS router. We're going to bring another router here. Now we've got two routers, everybody. Let's configure this next router. But while we're at it, let's make sure it works with router 1. So show IP int brief. And we need to make sure we know the IP addresses that are on this router. Okay, so let's set up router 2. And on router 2, we're going to make it connect Ethernet 0/0. So let's draw a connection between G0/0 over here and G00/G00. So we're going to get to subnetting tomorrow, but just in case you guys already know subnetting, let's go to this brand new router, router 2. Let's set it up to work. Let's make it work. It'll be fun. So router's coming up. It's booting. That's why it's slow. Let the router come up. We'll configure it. And then we did some configuration today too. I tend not to be Mr. Lab, but some of this stuff is just pretty important to know. This thing up and running? Yeah, it is. It's just still booting. Come on, wake up. Okay, so router's up. So let's boot it up. Let's have some fun. Let's change the host name. So if this device is called R1, what should this device be? Let's call it R2. Eva Dorkia, if you can hear me, I see there's some people that are trying to write some content on PIM and multicast. Could you share the document that I wrote 20 years ago while working at Riverstone Networks, which is used by every major company for IP multicast troubleshooting in the world? I know you found it somehow, Eva Doikia. I don't know how you found it. So if you can just share a link to that document, I think it'll be helpful to people that are interested on multicast. Because I want to make sure that we're accurate and correct. Because I can't really see what's going on there. So this device says router. So let's give it a new name. Let's call it router 2. Host name, R2. Oh, it's already changed. Now let's put a loopback address on it for management. So let's create a loopback interface, LO0. And of course, I typed in extra O. Now the interface by itself is going to be down. Let's put an IP address. Let's call it 2.2.2.2. Let's give it a 255.255.255.255. That's called a host root. Now, guess what? Did I put IP address? No. How do I get to the beginning of the line? Control A. Huh. Now I can just type IP ADDR because I forgot. Enter. Oh, wait. I made a spelling error. I added an extra dot. It didn't like it. And it even showed me with that little caret thing there where my mistake was. But still didn't like it. Why didn't it like it? Oh, wait. I forgot a dot and a 5. Now it looks right. Is it going to take it now? Yes, it did. So no shut. So there you go. Ivadoiki Pop, my intro to multicast document. And there we go. Now, this gigabit Ethernet 0/0 on the one side is different than this one. That's 172.16.1.1. So this one should be 1.2. Again, we're going to cover subnetting. So int G0/0 IP ADDR 172.172.16.1.2 255.255. I'm assuming that's the subnet mask I used. 255.252. Let's confirm on our previous router that I'm on that subnet, because if we have an address on a different subnet, guess what? It won't work. So let's just confirm that the link between them is on that. It's a /30. So we're here. We've got the right IP address. And guess what? We're going to turn on the interface. Now, do we think that interface is going to come up because it's now plugged into the router? Whoa, look at that. Line protocol gigabit interface up. So show IP int brief on the second device. Guess what we see? We've got a loopback address. And the loopback address is on there. And we also have the far end. So let's have you guys work through it. I'm going to give you your first networking troubleshooting challenge of the day. If this 172.16 is on one side of the link, 172.16.1.1, and on the other side of the link, we have 172.16.1.2. You guys think I can ping across the link? Do you think I'm going to have IP connectivity from one router to another router after I put them on the same subnet and we ran a wire? Are they going to be able to talk to each other, everybody? If you think so, put the answer yes in the chat box if I can ping across that link. If you think the answer is no, type no and why. Here's a hint. Same subnet. There's a wire between them. Can they talk to each other? Yes, they can talk to each other. As we've mentioned, we use EVE-NG Professional. That is the simulator we're using. They can talk to each other. Fantastic. Yes. Now, can router 2? Yes, they can talk to each other because they're on the same subnet. They're both on that same /30. So let's ping across and check it out. Ping 172.16.1.1. Can it reach it? Okay. ARP, who has the MAC address? And we can't. So what did we misconfigure? Did we put them on so show run? What did I misconfigure on this? Did we put it on a different subnet by accident? Nope, 172.16.1.2. And this one over here is 172.16.1.1. G00, G00. So this should be working unless we made a configuration error on one side. That's timing out too. So why isn't this link up? Gotta love doing live technology demos. I may have configured the wrong link. Let's give it a minute to see what's not going on between these two devices, because we should be able to ping across the link. We are not passing traffic over this link of any kind, layer 2 or layer 3. So we're on the same link on the same subnet. Something's not pleasant. Okay, we'll let that do its thing. Most likely, we just need to reboot one of those things for it to actually work. But that's the thing. What you can see is you can configure it. You can put your links on it, and typically they'll work. Now, there's no reason why that shouldn't work unless there's a challenge with the logical wire we just created, because that will work on anything. Now, what should not happen is we should not be able to reach the loopback addresses without turning on routing. So we probably should figure out what and why that occurred, and we'll get back to that. I'll go back and debug it a little bit, but I want to keep the flow. So let's go through the next phases of things here. Let's walk through the modes of configuration while we're at it, as soon as these devices come back up. So let's walk through the modes. And of course, our devices are still coming up. One of these guys will be up soon, and I'll be able to show you the modes. While we're at it, let's turn this device on. Oh, well, there's a very good reason we're not able to ping across the link. Can anybody tell me why we can't ping across this link? It's shut down. Let's turn it on. On routers, devices come from the factory. Shut down. So now do you guys think we can ping across this link? Ping ourselves first to make sure our address is good. Woohoo! Let's ping across the link. Why are we going to lose this first packet? Oh, let me just check and make sure that this is turned on this side too. Okay, that one shut down too. Okay, so now,
and Mike, can you pull that? I guess you would call it the bottom window up a little bit. Yeah, there we go.
Now let's ping across the link. Now the first packet's going to be lost and the second 4 are lost. Huh. First packet lost and the second packet's lost. Now if I repeat the ping, does anybody think I'm going to lose the next packet? I won't. How fast that was. Why was it that first packet was lost? Okay, so I'm on the device. ARP, who has the MAC address of 172.16.1.2? That ARP broadcast took about a second or two to get a response. That's why we lost that first ping. Note if you look very carefully, you get a period and then you get the 4 bangs. And then every subsequent time we get 4 bangs. So that first one was lost due to ARP. So I see a Jim Weaver there. I don't know if you're the same Jim Weaver I know from Cisco. If you are, it's great to see you. If you're in a different Jim Weaver, I'm thrilled to have you here as well. So we go back to these devices, everything makes sense. So now let's think about this. Will I be able to, from router 1, be able to ping router 2, this loopback address, the 2.2.2.2? Let's try it. Well, before we try it, let's do a show IP route. Do I have a route to 2.2.2? No. So is it reachable? No. But let's try it. Let's pretend we didn't know. Ping 2.2.2.2. Timeout. 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 Now, why can't it reach 2.2.2.2? Okay, Jim, you're the other for my class. Wonderful, fantastic, thrilled to see you. Why can't it reach 2.2.2? Because it doesn't have a route. So if you're a cloud architect and you can't reach something and you look in the routing table and you don't have a route, guess what? You're not going to be able to reach it. Now let's think about this. If I don't want to be able to reach 2.2.2.2 on this router here, if I don't give anybody the route to it, can they hack me? No. So no route, no path. No path, you can't be hacked. So when we start talking about security, and we're going to get into cloud security and network security, if you don't have a route, you can't hack it. So I want to go visit Ivadoika over there in Hungary, which is across the ocean. If I have an airplane, I can visit her. If I have a boat, I can visit her. But if I don't have an airplane or a boat, guess what? I can't visit her. Why? I don't have a route. So keep that in the back of your mind. So now I could put a route on this. I could put a static route that says to reach 2.2.2.2, go over that link. And guess what? If I made a static route over here, it would be perfect. I could put a route here and a route back. Why? There's only one link. There's no recalculation. But what if I wanted to make this smart? Let's just turn on some routing. So now you're going to see config T, router, OSPF. We're going to turn on a routing protocol called OSPF. I'll go into it in more depth. Network. Let's just say 1.1.1.1, 0.0.0.0, area 0. We'll be talking about how this protocol works in depth. I'll spend a full day on it. Then we'll take this network 172.168.1.1.0, and then we'll basically take this 0.0.0.3. I'll teach you what this means later. And on the other router, I'll do the same thing. I'll go to this router. I'll go to config T. I will do router OSPF 1. We'll do a network for the statement for the loopback. Then we'll do something for the WAN link, 172.1.6.1.0, 0.0.0.3, area 0. Let's see what happens now. Just enabled routing on 2 different devices. So let's going to see what's going on. Make sure we put the configuration in correctly. We put in some OSPF. We popped, okay, so neighbors didn't come up. Why? Is the network 126 or 172? It's 172, not 127. So if you type something wrong, what's going to happen? Show IP route. We're not going to have any. Now, if I change this and I do to router config T, router OSPF1. Now, if I add a network statement, let's remove the one. So if we had a network statement that says 172.16, and I have to type it right, 72.1.6.1.0.0.0.3, area 0, I'm going to tell this interface to participate in OSPF. Oh, wait, did you see this message? Look at this message. OSPF adjacency changed. Neighbor is full. Okay, now, if I do a show IP route on this device, look what we see. And if I do a show IP route on this device, what do you see? Now, before on this device, when you wanted to reach 2.2.2.2, you couldn't. Can you now? Yeah, you can. Why? It's in the routing table. See? You've learned 2.2.2.2. Now, this is router 2. So can we reach 1.1.1.1 on the other end? Well, it's in the routing table. If it's in the routing table, we probably should. Okay, we can. So now you're seeing that we're learning it. So what routing protocols do is they tell other people what the routes are. So let's go back to router 2, and for fun, I'm going to add some more interfaces. Int, loopback1, IP address, ADDR, 3.3.3.3, 255.255.255.255. Okay, no shut. While I'm at it, let me add another one. Interface loopback 2. Of course, it has to be. Let's see, Amy. Hold on. All right, now we're on router 2. So we just added 2 interfaces to this device, show, IP, int, brief. We added, remember before we could reach this and we could reach this, but we added 3.3.3 and 4.4.4.4. From router 1, does it know about them? Can router 1 know about these devices? Does it know how to reach these 2 devices? Well, let's look at its routing table. Show IP route. Wait, I don't know about 3.3.3.3 and I don't know about 4.4.4. Can I hack it? No. Can I reach it? Let's check. Now, if it's in the not in the routing table, here's the secret. You won't be able to reach it. It won't happen. No. Let's try 4.4.4. It's not in the routing table either. Is it reachable? Well, no, not at all. And you're going to see, we're going to talk about these things. So now I could put a static route on router 1 that says, hey, to go here, take this link. But the problem is if I have backup paths, so this is like me visiting Chris. I know to visit Chris, I've got to go take I-95. I've got to go make a left and go west to Tampa. And then once I get to Tampa, there's a certain things that I need to meander. And that's fine. I'm good with that, right? But let's say I printed them out like a static route and I've got a piece of paper in my car. And now the police have a roadblock up. Can I get to Chris's house anymore? No. So if I had a GPS in my car that knew every street, but it'd say, recalculating, make a left, make a right, go 46 miles, and then you're going to see Sonny the cat. So, my GPS has the intelligence, so the routing protocols can too. So let me show you how fast this is going to work. So we're going to do config T on here. We're going to do router OSPF 1. We're going to add the network 3.3.3.3 into OSPF 0.0.0.0, and we're going to put it in area 0. Is that going to be reachable here? Let's see. Let's look at the routing table. Nope, not yet. Look at that. 3.3.3.3 popped in the routing table. Can we reach it? Yeah. Can we reach 4.4.4.4? Show IP route. We don't have a 4.4, so let's try it. 4.4.4.4. No route. We can't reach it. Okay. Should we tell it about the route so we can reach it? Watch this. We'll go over here. We'll tell OSPF, which is a routing protocol, and we're going to talk a lot more about routing protocols, but I wanted to give you a feel for networking. 0.0.0.0. Wow, we're going to stick it in area 0. Now we're going to tell OSPF that we know. Now let's look out over here. Let's look in the routing table. Do we have it? Wow, 4.4.4. And how is it learned? Oh, OSPF. This 110 thing is going to tell you about administrative distance, which we'll talk about later. And this 2 is the metric of the route. So now can we ping it? Oh, we can. We have a network and it's fully functional. So now you get it. So let's talk about the configuration modes of these devices. So there's router, there's configuration mode. This is global configuration mode. There is interface configuration mode. How do we get to that? We pick another one. We go to interface loopback 0, where now it says config IF, interface configuration mode. Now we type router OSPF1. Now we're in router configuration mode. So keep that in the back of your mind. These will all be test questions, and they're all things that you need to know. So when we're dealing with routers and switches, we're going to have a bunch of different kinds of memory. We're going to have RAM, DRAM. It's the same DRAM that's in your computer. Same thing. And it's memory that stores the routing table, it runs the routing software, et cetera, et cetera. Now, in your computer, you have a hard drive, which stores your operating system. On your mobile phone, you have flash storage. What do you think Cisco routers use for storage? Flash storage, just like your mobile phone. Why? It's fast, it's efficient, there's nothing to break like new hard drives. So we have DRAM, we have flash. Now we have something called a ROM. And, like in your computer, you've got the BIOS that you boot into, the basic input-output system before you get into the hardware. Well, and that's like a bootstrap. Well, pretty much the ROM that exists on Cisco router is just like that. It's just like the BIOS in your computer. And somebody asked, where can we store the configurations? I think it was NitroPan. We store the configurations in something called non-volatile RAM. It's basically a form of flash, et cetera, and it stores the text files. What do these text files look like? They look exactly like this. If you do a show running config on a router, your text configuration is going to look like that, and that's it. It's just standard text, and that's what you're going to see there. How do you get the stuff that we're working on to the startup configuration? Well, we can do the old school CCIE is WR because it used to be write memory, but it technically is copy running dash config to startup dash config. That's how you save it, destination file name, etc. Same as my write memory, but it's the appropriate terminology, the one that Cisco actually recommends. Like I've been an architect for too long. I've been dealing with this stuff for too many decades. I may potentially use a different approach for those reasons. So basically, startup config runs in NVRAM. Your running config is running in RAM, no big deal. So the next thing, we showed you how to show the running configuration. And there we go. That brings us to chapter 5, which is, guess what? Is going to bring us into LAN switching and really, really, really cool stuff. So let's do this. I don't want to overwhelm you. I want you all to become great network engineers, great network administrators, great solution architects, great cloud architects, or whatever that career is that you want. So let's take some questions. And then after some questions, if you guys want, I can go a little more, or we can call it for the day. It's up to you guys. What's the loopback between a loopback and a regular Ethernet address? What a good question there, Sarah Ahmed. So Sarah, a regular address is a physical port. A physical port. A loopback address is a logical address that you put on the routers. Why do you put the loopback addresses on the routers? For the following reasons. You're looking for some logical address that doesn't go down. So when we connect to the cloud providers, they say, hey, we've got a high availability device because it's not a real device. It's just logical device that's created in software that can exist anywhere. So that's the difference between a loopback. A loopback is a management interface that we put on there. It is not a real interface. And we can assign any kind of interface IP addressing we want to it, including a /322. It's just there for management, router identification. Great question there, Sarah Ahmed. Chris, if you want to bring in the next one. Nitropan, what does area mean? Oh, Nitropan, we're going to have fun with this topic. So here's the key. When we deal with the Dijkstra routing protocols, whether it be intermediate systems to intermediate systems or OSPF, open shortest fast first, what happens is we divide our network into sections, and they're called areas. And the reason we divide it is inside of an area, you need to know everything about everything inside of that area. But in between areas, you don't need to know as much. So it gives us a means to decouple or segment our networks to make them scale. So I was looking for that question. Nitropan, that's an extraordinarily good question. We will spend 1 to 2 days on this matter of the areas, specifically for our cloud architects and our network architects that really want to do system design. Knowledge of OSPF is critical. So great question. It's part of the way we segment our Dijkstra-based algorithms that run that shortest path first calculation. Fantastic question there, Nitropan. The loopback is an address that will never go down. It's a management interface. So I want you to think about this. Let's go back to this example. Not this example, this example. So now that we're back into this example, watch what happens if I disable this link, like a cable gets cut. Hold on. Let me see if I can disable the link. Suspend the link. Okay, so the link just went down. Now that the link went down, oh, there you can see it. Here you can see what happened. Line went down, and OSPF noticed it. It took OSPF a little longer to detect the calculation. The link went down over here, and it took 10 milliseconds for OSPF to notice that the link was down. So that's what we're talking about. So, keep that in the back of your mind. So now, if I do a show IP route on this, do we have any of the routes from the other side? No, we shouldn't. Hold on. Why are we not going to have any routes? The link is dead. Watch now. If we go to this device, is the loopback address still up? Show IP int brief. Now notice our Ethernet port went down because the link went down. But notice that all our loopbacks stayed up. So you asked a really great question. So let's make the link come back up. Let's resume the link. Watch what's going to happen. OSPF is going to detect it. We're going to see a neighbor adjacency change. Watch it happen. There we go. Now, line protocol went up. Now, we should be notified of an OSPF neighbor change fairly quickly. What has to happen is the routers have to say, hello, 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 I'm here, you here, we're all here. So I didn't see an OSPF net, so show IP OSPF neighbor. I haven't seen it come up yet. Well, apparently the neighbor's up. We can see, and we'll get into this, but it's not completely up. Let's give it a minute. Let's see where the OSPF status is. 2A GR others. So let's look at the show IP route now. We're not seeing, OSPF just came up. Now, if we look at the show IP route, we're going to start seeing that we're going to get routes from the other side very quickly. We haven't gotten them yet. We're still calculating, still calculating, still calculating. Oh, now they came in. We can see the OSPF. So let me show you why we use a loopback, because right now it doesn't make any sense. Let's draw another link between these connections. Okay, so now let's do this. Let's pick another link between these connections. So on router 1, now we're going to configure one on gigabit Ethernet 0/1. So config T, interface G0/1, because we didn't use that one before. So in G0/1, so let's do an IP address, IP, ADDR. Let's say 192, did we use 192.168? No, we haven't. 192.168.1.1, 255.255.255.252. No shut. Now on this side, Let's configure this router. Config T. Interface G0/1. Of course, you have to spell it right. IP address. What did we use on the other side? .1. So 192.168.1.2.
Can you pull that window up just a little bit?
You got it. So now we added this. Let's Control E. Let's add a subnet mask 255.255.255.252. No shut. Now, when we shut this, when they're both ports come up, this port should go up. So can we ping across the link? Let's make sure. Ping 192.168.1.1. Okay. Why did we lose the first one, everybody? ARP! Who has the MAC address? And that's why we lost it. So let's go to the other side. Can we ping across the link now? Ping 192.168.1.2. Can we reach it? Yeah, we should be able to. Oh, well, the reason we couldn't is because I typed 192 as 129. So that will explain that. So let me retype this. Woohoo! Now the link's working. Now let's look at the routing table again because this is really important. If we do a show IP route, look how it's reaching everything. Gigabit 0/0, gigabit 0/0, gigabit 0/0. It doesn't know to use this link for anything. So how do we make this work? We go back. So we go to OSPF, router, OSPF1, and watch what's going to change. We'll do a network. We'll add this 192.168.1.0, 0.0.0.3, area 0. Now you'll see why we're creating a loop. Now you're going to see why we're creating the loopback. Config T, router OSPF1, network. Network 192.168.1.0, 0.0.0.3, area 0. I couldn't fly, but we'll see. What we expect to see if we did this correct, and I didn't make any spelling errors, we're going to see an OSPF adjacency come up, and we'll see in about 30 or so connection seconds. But let's make sure that I didn't, do a typo. Ah, look at that. We're beginning to form our neighbor relationship, and we'll talk about what these states mean. We're going to do it again. Oh, it's still filling up. It's still filling up. Let's see what's going on this side. Oh, wow. Look, we just formed a full neighbor, and we exchanged our stuff. So now we're going to look at the routing tables in both of these routers, and they're going to be very different now. I'll show you why. So now when you get to this router, do a show IP route. It'd help if I could type. Now, wait a second. Does the routing table look a little different? Go to this one. Show IP route. Now look at this routing table. It looks a lot different than before. Now for 2.2.2, which path do you have? Gigabit Ethernet 0/1 and 0/0. We have two equal cost paths now. So what happens if I want to form a neighbor relationship and I do ping 192.168? We do ping, yes, 192.168. 1.2. This is what's called an extended ping. There's a reason we're going to do this. Repeat. Let's change this to 100. Let's change this to 100. Datagram size here. Oh, well, that went a little faster. So, but what I wanted to show you is this. Right now, we're pinging across that link. But let's say right now we ping 8.8.8.8. That's not an address we have. Never mind. We have to pick an address that we actually have on the device. That would be my fault. So show IP route. Okay, you can see how we've got everything. So if we want to do a ping to 4.4.4.4, everything works great, right? Now, let's say we want to ping across the other end of that link, 192.168.1.2. That works, right? Let's say we've got a cable cut. So we would never use a single network provider. So one link is on AT&T and one link is on Verizon. The same way it would be insane to stick all of our things in AWS or just Azure or Google. We always want to use multi-cloud and multi-providers. We've been doing this for 30 years for this reason. So now this is your AWS or your AT&T link. That's dead now. So watch what happens. Can we ping the far end of that link? No, because the link is dead. We can't ping it. The link is dead. But now, do you think we can ping the loopback address? Yeah. This went dead. Why did this go dead? Because it's a physical device. The cable was unplugged. But this logical device, guess what? The reason it works is we rerouted. So let's bring this link up. Now, how long is it going to take for OSPF to discover each other and fully load? Well, line protocol's up. Let's watch it. In about a minute, we're going to get a notification from OSPF that the network is self-healed. Let's wait for it. Let's wait for it. Let's wait for it. Still coming up. We should form. So now let's look at the show. Let's go back to here. Let's go back to this router. Let's do a show IP OSPF neighbors. So IP OSPF neighbor. And what do we see? It's XStart, which is on the way to form, loading full. Now we've got full neighbors. Woohoo! So now guess what? We should be able to ping across the link. We should be able to ping the 192.168.1.2. We can also ping 4.4.4 because we've got two paths. Now let's take the top link. So we lost the AT&T link is up, but the Verizon link went down. This is why you should never use a single cloud. It's insane because this stuff's going to happen. Now, are we going to be able to ping on the other end of this link? We're going to be able to ping can we ping the 4.4.4? Watch what happens. Now the top link was the primary link. Now it's healed. Now notice we lost ping 1, ping 2, ping 3, ping 4 in the process, but now we got them all. Now let's bring the link back. Resume link. Okay, right now, can we reach it? Let's see. Can we reach it now? Yeah, because we're using the backup link. Can we reach it now? Can we reach it now? Yeah, we're reaching the backup link. Can we reach it now? We're reaching the backup link. Can we reach it now? We can still reach it. We can still reach it. Now we may lose connectivity during the healing for a second. Maybe not. Let's see. Still getting all these pings here. Fast. Guess what? We haven't lost anything. Why? Because we have two links on a different service provider. That's why never, ever single cloud, or never, ever buy all your links for Verizon, or buy all your links from BT, or AT&T, or NTT. That's why we always recommend two links on two different service providers. So now you know that's why we orchestrate networks the way we do. Whether it be networking or clouds, we should never allow a single plane of failure. And 1 is none, 2 is 1, and 3 is greater than 2. So we talked about a lot of stuff today. I'm sure there's some questions. Let me answer the questions and let's call it a day so you guys can get some refreshed and come back tomorrow and become strong. I want you guys all getting the best cloud architect jobs, solution architect jobs, network engineer jobs. And that's why we're doing this free CCNA training, the Cisco Certified Network Associate training, CCNA 200-301. Here's the thing. This is the foundation of the cloud. Know the network and you know the cloud. And I want you all getting, guess what? Hashtag cloud hired. So Chris, bring in the last questions and then let's let everybody have a good night's rest so they can have a good night's sleep. And we'll get back to it, hardcore networking tomorrow. It'll be fun. Can I please make some more summary? Sure. Networking is about the connectivity between two or more locations. Network devices include routers, which take your information and direct your traffic through the internet. They include switches, which we'll talk a lot about how the switches and bridges work, which we'll have lots of fun with. We talked about today WAN technologies such as serial ports, HDLC, frame-relay, ATM kind of things. We talked very briefly about LAN technology. Actually, we spent a lot of time talking about Ethernet, Ethernet frames, Ethernet headers, etc. We talked about using some network diagnostic tools such as ping. We talked about the router and switch configuration modes. We talked about user mode, enable mode, or privileged executive mode. We talked about interface configuration mode and router configuration mode with regards to the OSPF that we did. We introduced basic routing. We introduced basic routing tables. We introduced routing logic, the hot potato logic. We talked about how we map layer 2 addresses to layer 3 addresses with this really cool protocol called Address Resolution Protocol called ARP. We covered the OSI model. We covered the internet model. We covered how to access Cisco routers, 9600, 8, and 1. Why do I say that? It will be at least one test question, and I want you all to get it right. So these are the concepts we kind of talked about. So if there's any questions you'd like, Chris, let me bring the questions. We may not be able to answer all, but I'd like to help with some. I want everybody to have an incredible experience. Gus, the engineer. Mike, in terms of layer 3, how many layer switches are used for routing? Gus, the engineer, back in 1998, we used to do this crazy thing called router on a stick, which I'll talk you through, where we basically had switches that were layer 2 and routers that were layer 3. Around 2000, every switch that I've ever worked with was a layer 3 switch, and it was being used for routing and switching at high speeds and high performance. So I don't do a lot of layer 2 stuff. The only kind of layer 2 switches that I even have are these kind of things like me that I have running through my house. And basically the reason I have these layer 2 switches, Gus the engineer, is I'm running a private cloud, an OpenStack cloud here, and I've got a bunch of servers that I aggregate into these switches, which that get plugged directly into my router. And I'm running very high performance routers here that in this house. So yes, lots of layer 3 switches used for routing. And somebody asked a question about a trace route. We're going to get into that heavily, but I can show you a little bit about a trace route if you desire. But what we can do with it isn't going to be very useful until today. But I can show you a little bit about what it would do. So if we're on router 1 and we wanted to see how to reach 4.4.4, we would do a trace route, and it will show us the path. Trace route 4.4.4, and it's going to show us the path that it takes. And what would ultimately happen is, as it's showing us the path, it's going to tell us exactly how the path to get there. So let's see what it tells us. It tells us the first hop is this interface. And it tells you the next hop is here. And this is the third hop, which is the destination. So why is that important? Well, it's a great question you asked. So I didn't mean to do that. If I were to add another router, let's say I pop another router over here, and we draw a link between these two routers, and we turn this router on. Real quick, we'll just make a quick interface, and I'll show you what I mean by the full trace route. Because that's a great question. It's going to take a minute for the switch to reboot itself. Switch you up. Okay, let's go to this new device. Here we go. We've got a new device over here. Let's make sure it's ready. We can do this pretty quickly. I'm going to do some quick configuration of this by taking a couple of networking shortcuts, which I'm not going to recommend you guys do, but just for the speed and precision, we'll avoid any of the math, just to make it clear. So I'm going to configure this third router in, relatively fast speed. Okay, come up device. This reminds me of the processors when they were 25 megahertz and we had 16 megs of RAM. Okay, are you up? Come on, work with us. Please work with us. I love this question. Okay, so we're never going to do this crazy dialog box. So here's what we're going to do. We're going to let it come up. We're going to do a real fast configuration of this device. All right, so okay, enable. So let's give it a name, config T, host name, rar3, int, hello, oh, let's put a loopback address on it, IP address. .8.8.8.8, 255.255.255.255. No shut. Now, what's the link on this device that connects? Int G0/0. Help if I didn't put the O. Int 0/0. Let's say IP address. We're going to do 192.168.2.2. 255.255.255.252. No shut. Let's do router OSPF1. That's basically going to put everything into OSPF in a single command. That is not something we would normally do because we want security. But what are we trying to do over here? We're trying to work real fast to just create an interface. Now let's go back to router 2. And router 2, what is the Ethernet port that's connected to that? All right, let's just do. Router 2 is on the opposite side of that sign. So config T, interface. What do we have at G0/2? IP ADR 192.168. What was the address we used? 2.2. So let's make this 2.1, 255.255.255.252. No shut. Router OSPF1. Network 192.168.2.0, 0.0.0.3, area 0. So if we did this right, our ports are going to come up. We'll be able to ping across the line, and we're going to form a neighbor adjacency directly over that connection. So let's see if we did. Show IP route. If router 3 knows how to reach, it can. So router 3 can ping 1.1.1.1. But what if it couldn't? What we would do is we would do a trace route to find the path. And watch, it's gonna give us the sequence. It's gonna show us the path. So the path is gonna work right now, and you're gonna see it. But what happened is if we were here, and our data made it to here and then got lost, we would know to go to this router to see where the problem is. As you can see the path. It's mapping out the path for us. And then Chris has a few questions, which I definitely want to ask, sir. But you can see the path and how directly it gets there. There you see. That's what the trace route is, and that's the function. Chris, I know you had some questions for me. Okay, I didn't see the first half of the question, Chris.
They want to know, as an architect, am I going to be configuring? And the answer is no.
The answer is generally no.
And so this is the follow-up.
Okay, so why are you learning how to do this? Well, if you don't understand the routing tables and the routing information, you'll never be able to design anything as a cloud architect, because the network is the foundation for everything. Why am I doing this? Teaching this basic networking configuration? Well, I can tell you that if you just had an AWS certified solution architect professional, it's not enough to get hired. And the thing is, as an architect, you have to have the internal knowledge. You have to know how it all works. And this networking thing is really, 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 really theoretical. So I'm giving you the configuration so you can see it. Now, here's the thing. When you're building a certification portfolio for a cloud architect, and by means, certification does not get you hired, it's everything else that does, but certification will get you an interview. And on the interview, they love to see infrastructure background, like networking or Linux. So how do you get a networking certification? You have to know how to do this. So what looks good for an architect? A network certification, an architecture certification, an MBA, leadership, emotional intelligence, executive presence, et cetera, ROI modeling skills. But networking is the heart of the cloud. And if you don't know the network, you don't know the cloud. So why am I teaching you networking? So you learn the foundation. So when somebody asks you, hey, have you ever set this up? You can say yes. Why do you think I make my students build a cloud? Because when they tell their customers, I've designed and deployed an OpenStack cloud, the customer takes them seriously. So if they say, have you done it? And you say, no, it doesn't look good. So the answer is, yes, I've done it. But my background is design and digital transformation. But if they ask you if you've done it, I want you to be able to say yes. So that's the reason why. Yes, every device has an ARP cache, and the ARP cache is, you can configure how long it stays in memory. Absolutely. The longer the cache stays in memory, the less overhead and broadcast. But the more stale data can be there. So you got to remember that. And that's always the problem with the cache. But great question. Yes, routers have an ARP cache. Excellent. When you copy the running configuration in the router to the startup configuration, it stores it on the flash. That's it. Should we download my simulator? You can download my simulator. You can buy my simulator, and you can do like I did. You'll have to purchase the software for the devices. So you can do it, but realize it's going to cost you a fair amount of money to set it up properly. Layer 3 switching works completely at layer 3. What happens is we're going to create a VLAN, and we're going to give it an IP address, and the ports are there, and it is 100% layer 3, no different than a router. It's just that it's routing in between VLANs as opposed to routing in between physical ports, but it's 100% layer 3. Now, CT scanner, you're going back to WAN interfaces like serial interfaces, and they have data termination equipment and data communications equipment. But for the most part, we rarely deal with that stuff anymore. And that is provided by the service provider, typically speaking, in their DCE device. But the point is, I think it's DCA, DTA, but whether it's the termination device, which is your router where you're connected to, the clock rate is always supplied by the carrier, your service provider, that based upon the bandwidth that you've purchased. That's your clock rate. Now in labs, people set the clock rate, but in reality, it's done by the carrier. Yes, those blue rations are awesome. John Clark, I don't normally use acronyms, but if I said open shortest path first, that wouldn't mean anything to you until we talk about the open shortest path first routing protocol. So it's typically called OSPF. I don't know of anybody that uses the name open shortest path first. Kind of like very few people would say, today we're going to work on the border gateway protocol. In fact, they call it BGP, and that actually became known as its new name, its official name. So what are some of tomorrow's topics? We've got so much to cover. We haven't even begun to begin. Some of the things we'll probably cover tomorrow. And, I have to tune what we cover based upon, realistically speaking, what people are paying attention to. And I'm going to go back and forth based upon things. But what are we going to be doing? We're going to be talking about a lot of LAN switching. In the beginning of the day, we covered some basic routing. And then after we cover switching tomorrow, we're going to talk about remotely managing switches, and we're going to get our hands dirty playing with some switches. And then depending upon how far that goes, I'd like to get us into some VLANs tomorrow too. So happy to provide this training. Thank you so much for coming, Anil. Was thrilled to see you here. What is G0/0, G/1? That is the physical port numbers on the routers. So all these devices will be logically based on slot number and port number, and that's just the way they refer to them. If you go on your computer, you'll have an ETH0, an ETH1, an ETH2, based upon how many network cards you have in it. That's all it is. Good question, though. Sadie, I'm so happy you were here. Was thrilled to see you. I'll see you tomorrow. Mohammed, thank you so much for contributing. Everyone contribute. Thank you so much for being here. Sadie, yes, thank you. Thank you. All my blue wrenches, they're amazing. Thank you, Chris. And William Byrne, I am actually so happy to see you here today. At some point, you and I should sync up. I know you've got all kinds of great backgrounds, and I love to talk to you about that. Millicent, I'm so happy to see you here. Yes, it's all about competency. Why am I working so hard to make sure you all have the underlying technical knowledge so you're competent? Everybody type hashtag CCNA one more time. And when you're done with that, type hashtag cloud hired, because that's kind of our thing. Thank you, Pedro, for thanking Chris. Chris does so much work. Eric, we are so honored and privileged to be able to help make sure people have the best careers. We're looking forward to tomorrow too. Yes, please like, comment, share. We really love that. We really want to share our message. Abigail, thank you so much for everything. And I think I saw a blue wrench, so thank you as well. Jal, so much. Marjan, so good to see you. Anil, great to see you. Nosa, so wonderful to see you. Leo, thank you so much for helping out as well. John, thank you. And yes, thank the blue wrenches. Thank you so much, Remy. We're going to start getting into more fun stuff when we talk about routing, but we've got to start somewhere. You're here. Yeah, we could talk crypto one day. I like talking crypto. I've got a lot of blockchain background. Thanks so much, John. Rosha, it's always good to see you. Have a good night. Alex, Yasas, it's good to see you. Marla, thank you. CCNA. Ivadaikia, CCNA. Hand of God, good to see you. CCNA. Casigo, so good to see you. Remy, good to see you. CCNA. Ivadaikia, Marla, wonderful. Abigail. Okay, so wonderful, wonderful, wonderful. Super honored and privileged. Grateful to have you all here. Honestly, it's just wonderful, wonderful, wonderful. And I'm just thrilled to see you. So let's get you all network hired, cloud hired, whatever you like. Let's make sure you've got the skills to be great at your job. We are covering 80% of the certification, but as you notice, I'm not exactly sticking to the certification things because I want you guys getting network hired or cloud hired based upon what you want. So I want you to be competent. Certification and competency aren't even in the same universe. I'm concerned about competency for you because that's what's going to get you hired. Loving seeing these names from all over the world. Actually, maybe for fun, tell us where you're at in the world right now. I know we've got a lot of people from all over the world, and I absolutely love this. Wow. Las Vegas, Amsterdam, Australia, South Africa, Nashville, Australia, Brazil, Atlanta, and Detroit. We'll keep the Detroit. UAE, that's a place I've spent a lot of time and absolutely loved. Las Vegas, fantastic. Cayman Islands, Cornelia. Oh, wow, you're in a beautiful spot. Winnipeg, fantastic. Haven't been there in a little while. Nigeria, fantastic. We welcome you. Asheville, North Carolina, fantastic. Atlanta, this is great. New Mexico, Moses. Germany, Anil. Gabriel in Zambia, fantastic, Gabriel. Wisconsin from MJ. I love this. I mean, how many people we can get from all over the world, all coming together to make each other's life. Can you get this live again? You can watch this recording as many times as you want. We're going to leave it on YouTube. Share the wealth, spread the word, help as many people as possible. UK, Hand of God, I like that. Derek you're in Atlanta, Derek? Wow, for some reason. Molly's in Nigeria, I love that. Maryland, US. See how diverse we are? Charlotte, North Carolina. Cameroon, fantastic. Kansas, Maryland, Bridgeport, Connecticut. In Maryland, wow, this is great. Fantastic. So I will leave you all with, we're going to have some fun tomorrow. We're going to have a networking party tomorrow. So get some rest, relax. Atlanta, fantastic. Mexico, I haven't been there in a year, so I love it. Florida, fantastic. That's where I'm at. My advice for you preparing for the CCNA is as follows. Follow this course, and like we said in the beginning, buy the 2 Cisco press books, for which case we gave you the link to it, and that's all you need. You're going to be in great shape. Chris, you want to bring in the next question? Okay, fantastic. So thank you all so much. Have an absolutely wonderful night. Get some rest because we're going to hit it hard. We got about 7 more days first, so I don't want to burn you out. I want you to become great network engineers, great network administrators, guys, cloud engineers, cloud architects, whatever the career of your dreams is. See you all tomorrow. Have a wonderful, wonderful night.